Young researchers and beloved students. A warm welcome to you all to the second day of the International Conference on Advances in Statistical Methods and Applications, organized and hosted by the Department of Statistics, University of Madras. I now invite Professor Anbuparam, Senior Research Fellow and Statistical Genetist at the Center of Brain Aging, School of Psychiatry, University of New South Wales, Australia, to chair the Professor K.N. Ponusamy Endowment Lecture and say a few words about Professor K.N. Ponusamy.
Good morning to you all, respected professors and my dear senior colleagues. And
Professor, you are inaudible, please.
Am I audible?
Yes.
All right. Yeah, it's my honor to say something about this endowment lecture and about Professor Ponusamy. I was a student and later I worked under him as a technical officer. I would first read his bio, a short bio shared to me by Professor Suresh Chandra. And probably you should use it for future purposes as well. I think you have to give it to people who want to use this for future references. And then later on, I will record about my personal experiences with him, briefly, of course. And then I will have to introduce Dr. Sendamare Kannan, the speaker of this session. Professor Ponusamy was born on May 12th, 1940 in Kolathupalayam, a village in Erode district of Tamil Nadu, India. After his secondary education in Diamond Jubilee High School in Gobichettipalayam, he studied BSc in the PSG Arts and Science College, Coimbatore. In fact, I did my BSc from the same institute. In that sense, he is a super senior to me. He then attended Presidency College, receiving his master's in 1966. Subsequently, he moved to the Indian Agricultural Statistical Research Institute in New Delhi, where he completed his master's again, MSc Agriculture Statistics in 1968, and then he did his PhD and got his PhD awarded in 1971. His thesis entitled Some Contributions to Trial and Partial Trial Matching Design was written under the supervision of Professor M.N. Das. His research areas of interest include design of experiment, inference and variance components, statistical genetics, and computer applications. In fact, the statistical genetics concepts he introduced to me helped a lot in my career later on. After receiving his PhD, he continued at the Indian Society of Agricultural Statistics in New Delhi as a research statistician until 1975, from where he joined the Faculty of Agriculture at the Banaras Hindu University, Varanasi. He came to the Department of Statistics at the University of Madras, Chennai, in 1976 and stayed there until his retirement in 2000. During his 25 years tenure there, he also served as the head of the department for the period 1983 to 1999. After his retirement, he joined DNA Print Genomics, private genomic consulting faculty in Sarasota, Florida, USA, where he was a vice president. During his long and illustrious academic career, Professor K. N. Ponusamy supervised 12 MPhil and 14 PhD students, some of whom have received national and international awards. I would add that a lot of his students are well placed and well settled in life, in career as well. So under his leadership, the Department of Statistics at the University of Madras made considerable progress and achieved the status as an advanced center of excellence in teaching and research. He published more than 50 research articles in the national and international journals. During his tenure as the head of the department, he was instrumental in creating and implementing programs, including implementation of the MCA, Master of Computer Applications at the Institute of Correspondence Education at the Madras University through the distance education mode. So this is a brief bio of him, but I would add my personal experiences with him. In fact, I was his master's student and MPhil student, and then I did my PhD under him. So I was associated personally with the University of Madras Statistics Department from 1985 until 2003. I was a faculty there. So I would say, the experience at the University of Madras was immense to me, and it helped me later in my career. So I would also try to record here that that's the period where he was the head of the department at the Department of Statistics is the best period for the department, and not to underestimate the contribution made by the HODs followed him. I'm just trying to mention that the momentum for growth was set by Professor Ponusamy and his team. So in fact, the faculty strength at that point of time was full, and there were a lot of full-time research scholars. The research scholar room, now the computer lab, used to be full with many this MPhil and PhD students, buzzing with a lot of research activities. So I really miss that the time when I spent my time there. So he had, of course, had a lot of collaborations and brought eminent researchers to our department and make them present lectures in the department. So that was the occasion where a lot of people visited our department, and we got to know how the research is to be done. He had a great respect for his group. Of course, he brought Professor M. Das to the department on few occasions. And I would say that he was instrumental in bringing our first computers to the stats department. In fact, when the university got 1 or 2 computers, he made sure that stats department got the computers, and we had the first experience of using computers from at the Department of Statistics. The computers were not popular at that point of time. And he was instrumental in starting the actuarial diploma course, and then later on it became a master's course under Professor Gopal, and so he initiated a lot of interesting things at the Department of Statistics. So we used to wonder about his teaching and in-depth knowledge of the subject. He never brought notes to the classroom. He used to go for an hour, for hours and hours with a lot of information, without break. Sometimes other professors will come and lock the door because he doesn't stick onto the schedule usually. So I still remember his teaching on linear models and variance components model. In fact, he motivated me to do PhD under him on variance components models. So that's the experience that helped me a lot later on in my career. He's one of the favorite subjects is computer science, apart from statistics. He has taught us the fundamentals of programming, and he taught us Fortran program himself to us. His insights on the fundamentals of programming and helped us to learn the language, as well as it's now easy for me to learn any other language because the fundamentals he taught us helped me a lot. So I still enjoy the basics of programming which he inculcated in us. It still helps me. In fact, whatever I learn on programming is from the basics I learned from his teaching. So in terms for if I have to record on the research per se, so we used to work late hours, and in fact he used to sit with us late hours, sitting with us, debugging the code, whatever we write, and he helped sitting with us to write the simulation code, etc. So people at that point of time used to talk about the work culture at the stats department those days, because we used to stay late in the evening and we were very popular, I would say. So, but he's also a very kind-hearted person. He used to help the students out of the way and the faculty. In fact, he used to spend his own money to give us some tea biscuits. He used to take us with him to the tea shop, etc. So it's a great, it's a pleasure for me to recollect all those things, those golden period in my life. So I record my sincere gratitude to all the things he has done to the department, the statistics community, and personally to me. I wish him all the good health. Thank you.
Sir, thank you very much, sir, for your nice words about our process and your past memories. Thank you very much, sir.
Thank you. So should I now introduce Dr. Chandamari Kannan?
Yes, sir, please, sir. Yes, sir.
Okay, so it's my pleasure to welcome and introduce Professor Chandamari Kannan, a good friend of mine, and probably he's a senior, I don't know exactly, but maybe to me. And I used to visit this department whenever there is a chance, and he's very kind to me personally. And in fact, he's kind to other people I know. So he's now, he has sent a very short and sweet CV, so I'll go through it. So he's a senior professor now at the Department of Statistics, Mananmaniam Sundaram University. He's also Dean and Faculty of Science. So he had his PhD from Annamalai University in 1994, MPhil in 1989 from Annamalai University, MSc in 1987 at the Annamalai University Stats Department. And I now understand that he did an additional 2 master course, I think, MTech and CS and MTech in Computer Science and IT in 2009 and CS and IT in 2016, I think, from Mananmaniam Sundaram University. It's very interesting to know that he has done additional degrees as well. So he joined as a lecturer in 1991 at the Department of Statistics, Mananmaniam Sundaram University. He had the post of reader in April 1998. And then he was promoted as professor in 2006. And then senior professor in 2016, the same Department of Statistics. So he's now a senior professor, and he was instrumental in making the department from the scratch. I mean, whatever the facilities now they enjoy is a teamwork, of course, but he was instrumental in making the department. I really wonder on the progress they have made. So he had a few honors and awards. He got his BSR one-time grant by UGC in 2012, Young Scientist Award in Tamil Nadu by the Tamil Nadu State Council for Science and Technology in 1996, SCRC Visiting Fellowship by the Department of Science and Technology, Government of India in 1999. He is a recipient of Academic Excellence Award from Mananmaniam Sundaram University in 2008. His research area includes stochastic process queuing theory, biostatistics, time series, outliers, data mining, image processing, and its applications. He has published around 184 research articles, and he has authored around 10 books. That's his brief CV. And I'm happy to be associated with Professor Sandamari. Let's all welcome him to for his lecture. Thank you.
Good morning. Is it audible?
Please come closer to the mic, sir.
Good morning to all. Is it audible, sir?
Yes, sir. Yes, sir.
Thank you, Professor Angupalam. It's giving a good face to me. But it is a great opportunity to me because Professor KNP is inspired a lot from me during the 85 to 94. At the time, you are all research scholars. I'm doing MPhil in Annamalai University. Professor KNP is a good person for inspiring, particularly research scholars. During those days, Professor Andupalam is rightly pointed out. He is first Madras University is initiating the MCA program during that period. He only motivated research scholars to interact with the research scholars for the discussing for the research papers. During those periods, when I was studying MPhil in Annamalai University, we visited Madras University. Professor Andupalam is rightly pointed out that room is a very small room, but the scholars, MPhil and PhD scholars, is nearly more than 25 scholars are sitting in one room. They are all discussing in different subjects. Really inspired during those days. Around 87 to 88 or 89. Professor Karthikeyan and Andupalam and Ravanan, all are discussing different subjects. So really, it is the inspiration in this department. Professor KNP is extended in all type of help for the scholars, particularly in rural background peoples. I'm not directly contacted Professor KNP, but during the 92, in my selection, in my appointment, I'm working here for the temporary appointment. He is motivated, he is encouraged, he is giving the good encouraging words to, at the time of Vice Chancellor, Madam Vasanthi Devi. After the interview is over, Dr. Vasanthi Devi is personally giving a lot of information from KNP. So really, it is a great opportunity. Andupalam sir சொன்னாரு சீனியரா ஜூனியரான்றதுல சீனியர்னு சொல்றதை விட அன்புப்பழம் கிட்ட நான் நிறைய கத்துக்கிட்டேன். நான் அவர் அங்க ரிசர்ச் ஸ்காலரா இருக்கும்போது எப்படியெல்லாம் ஸ்டூடெண்ட்ஸ் வந்து இன்டராக்ட் பண்ணணும், ரொம்ப how the students எப்படி மோட்டிவேட் பண்றது, எப்படி ரிசர்ச் ஸ்காலர் வந்து ரிசர்ச் பேப்பர் எடுத்துட்டு படிக்கிறது, எப்படி டிஸ்கஸ் பண்றது, எப்படி எல்லாம் क्वेश्चंस கேட்கறது, அதெல்லாம் நிறைய இன்ஃபர்மேஷன்ஸ். அதுக்கு அடுத்தது வந்து பர்టిక్యులரா இப்போ ப்ரொஃபசர் கேஎன்பி பத்தி சொல்லணும்னா, அங்க during those days it is very rare for operating computers. Even seeing computer is also very difficult. In Annamalai University, it is only one PC is available, but at the time of Madras University, more than 10 to 15 PC is available. All PC is with the control of research scholars. Anytime research scholar is visiting the lab, he immediately access the computer facilities. So during that is the motivation for in this department. We proudly say that Madras University போல நம்ம டிபார்ட்மெண்ட் இருக்கணும்னு தான் நாங்க ஆரம்பத்துல நினைச்சது. உண்மையிலே really during those days அந்த 85 to 90 ல அவ்வளவு தூரம் அந்த டிபார்ட்மெண்ட் நல்ல ரிசர்ச் ஸ்காலர்ஸ் நல்லா யூஸ் பண்ணிட்டு இருந்தாங்க. Similarly, there are lot of professors. Professor J.R. is whenever he visited Annamalai University during that time, he motivated, whatever it may be, we discuss with the process. JR, he immediately motivated. Okay, very good result. Continue publish I will. So in this occasion, really, I'm giving my salute to Professor JR as well as Professor Sureshchandra. Is very sound knowledge about distributions and stochastic process. He inspired a lot during those days. So in this occasion, I salute Professor Sureshchandra. And during those days, Professor Viswanathan is also very giant. He is now no more. Now I salute Professor Viswanathan and his family. And Professor Gopal is always with us from the insufficient days. So I salute Professor Gopal for giving this great opportunity. Now I come to my topic. That is, my topic is just for overview about the outliers. This is the not new contribution to share some of the ideas for the young scholars, for young research scholars, for budding research scholars, or some of the eminent scholars to switch over your field. In this aspect, I'm just share some of the ideas for the outliers. My topic is outlier detection in high dimensional data, but anyhow, it is most of my slides, most of my PowerPoint presentation is just for the basic idea for outlier. What is outlier? What is the motivation of outlier? How? Is the slide is visible?
Yes, sir. Visible, sir.
Okay.
Visible.
Okay. Nice. Please. So thank you for giving this opportunity once again, and the Madras University, present HOD Sindhumor and his team, Dr. Suresh, Dr. Dharma, Dr. Ramadurai. Thank you for giving this opportunity to sharing some of my thoughts, my views regarding the outliers. Thank you for giving. Professor Andupalam, thank you for sharing in my session. It's a very great honor. Thank you, please. Outlier detection in high dimensional data. What is outlier? An outlier is an observation that lies on an abnormal distance from other values in a random sample from a population. You see the two pictorial representation. The red figure is outlier. Similarly, the second picture, the red dot is called outlier. The value that lies outside is much smaller or larger than most of the other values in a set of data. This outlier. For example, let us take these things. The one observations, one sample is very deviated from the all observations comes from 1 to 5. The one is very close to 10. So we suspect that this is outlier. For example, in this score 25, 29, up to etc. Here it is very inconsistent of the data 3 and 85 will be a very low as well as very abnormal. We suspect as these two are outlier. As per there are two pictorial representations. One is for fish, the red fish. It consists of 3 or 4 colors. This only one red fish is available. So we suspect that this is outlier. Similarly, the egg case. This is also there are all are coming from one category. One is called or white. We suspect this is outlier. As per the Hawkins 1980, he observations which deviates so much from other observations as to arouse suspicion. It was generated by a different mechanism. This is also outlier. It is a black sheep. This is called outlier. That black sheep. Next. Who is an anomalous person is called outliers. You see this is one. This is called outlier. This is also what to do that point destroying the curve. So now we discuss about, we think about how can this dot will be either destroyed, or it can be included. This is the major issues, basically. So the easy way is erase it or destroy it. Next. These are the one of the real life example. The following histogram displays the magnitude of 460 earthquakes in California occurring in the year 2000 between August 28 and September 9. Identifying the outlier on the very far right edge of the display beyond 4.8 in x-axis. You see a low bar. This represents one earthquake because the bar has height of 1 that was much more severe than the others in the data. Understanding the outlier, in this case, the outlier represents, in this example, I try to explain identifying outlier as well as understanding the outlier. Understanding the outlier, in this case, the outlier represents a much stronger earthquake, which is relatively rare rather than the smaller quakes that happens more frequently in California. The best act is one of the easiest exam. Easily understand all the budding scholars. The best actors Oscar winner example. The data is given for the age. We first look at the histogram of the ages of best actors, Oscar winners. There were 3 observations that looked like possible outliers. Then Q1 equal to 32, Q3 equal to 41.5. Given interquartile range 9.5. That is Q1 minus 1.5 plus or minus 1.5 interquartile range is 17.75. Another one is 55.75. There are 3 observations: 61, 74, and 80. The smallest observation is at 21. The main motivation of the outlier analysis is it can be in different perceptions. On the basis of the computer science engineers or some of the engineers easily approach these are the motivation of the outliers. In fraud detections, this credit card or telecommunications or criminal activities in e-commerce. These are all the under comes the umbrella of the product detection. Another one is called customized marketing, either high buying habits or low buying habits. Then medical treatments, unusual response to various drugs. On the basis of the pharmaceutical manufacturing industries, they use in this kind of applications. The analysis of performance statistics and professional athletes are using these kinds of these are the motivations. Then weather predictions as well as financial applications, either loan approval or stock tracking. There are different authors using the different definitions. As for the Hawkins 1980, an outlier is an observation that deviates so much from other observations as to arouse suspicious that was generated by a different mechanism, as per the Hawkins definition. Then Barnett Lewis is a very good book, John Wiley edition. There are 2 editions available. An outlier is an observation or subset of observations which appear to be inconsistent with the remainder of the data sets. Then Moore and Metcalf 1999, an outlier is an observation that lies outside the overall pattern of the distributions. As for the Chen et al., outliers are those data records that do not follow any pattern in any outliers are those data records that do not follow any pattern in an application. These are all the different definitions. These are the sources of outliers. So there are the possible sources of outliers are recording and measurement errors, incorrect distribution assumptions, unknown data structures, or novel phenomena. Recording and measurement errors are often the first suspected source of outliers. You see, the figure 1, the effect of assumed data distribution of the presence of apparent outliers. There are different sources of variability. As for the Anscombe 1960 in Technometrics Volume 1, he just pointed out these things. Sources of variability is maybe differ, explained as a 3 classification. One is called inherent variability, another one is called a measurement error, the third one is execution error. These are all the main sources of variability as per the Anscombe 1960 Technometrics Journal Volume 1. These are all the pictorial representation. All are comes under the same height. Only one person is a very abnormal height. These are all the inherent variables. Measurement error. All under comes under either the exact number is a 4.8 centimeter. In some of the can identify as either 4.9 is the perfect. Some may be 4.7. These both two as the outliers. This the outlier name is called measurement error. The execution error, the total error is a 5% point. It may be either bias or sampling error. These are all the treatment of outliers. As for the Barnett and Lewis book, it is clearly explained the treatment of outliers. The source of variation, the measurement, and the nature of outliers, random, and the manner of treatment is the test of discordancy. Test of discordancy, after the manner of treatment, maybe incorporate or identify or reject. These are all the actions. But normally nowadays, these are the, as per the Barnett Lewis book says, these are all the treatment of outliers. But nowadays, most of the researchers are using the after test of discordancy, first identify the outliers, then after they incorporate the outlier, then reject the outlier. These are all the nowadays, most of the researchers are following these things. Using the test of discordancy, then identify either your data set is involved in outlier. The first identification is the major issue. After identifying the outlier, either you should incorporate the outlier is the one of the main actions, or you can reject the outliers. So what are the consequences? What are the issues will be either reject or either incorporate. This is the major issue for the nowadays in research problems in both the computer science and statistics point of view. These are the various types of outliers. There are mainly it can be point outlier, contextual outlier, collective outlier. There are 3 types of outliers. The example of the point outlier, the picture representation is it is N1, N2. There are 2 clusters, and it can be the 3 outliers. Outlier 1 is only 1 point, and outlier 2 is also 1 point. It is very close to N2 set. It is also very deviate to N1 set. So the outlier 3 consists of 5 outliers or 5 points. These are all the point outliers. Then contextual outliers. Then contextual attributes. The contextual attributes are used to determine the context in the neighborhood. For instance, for example, in a spatial data set, it's a very more application oriented. It is a spatial data set, the longitude and the latitude of the location and the contextual attributes. In time series data, time is the contextual attributes which determines the positions of an instance and the entire sequences. Behavior attributes. The behavior attributes define non-contextual characteristics of an instance. For example, in a spatial data sets, describing the average rainfall of the entire range. The amount of rainfall at any location is a behavior attributes. It is not for uniform in all the places. The collective outliers. If a collection of related data instance is anomalous with respect to the entire data set, it is termed as a collective outlier, the outlier sequences. There are different causes of outliers. I just point out only 3 main causes. The poor data quality or contamination. The low quality measurements or malfunctioning equipments, manual error. The correct but exceptional data. These are some of the researchers are using the univariate tests. These tests is detailed available in most of the literatures. Groups test, Tingen mode test, generalized extreme standardized deviation test, Dixon test, Humble's test, quartile method, precise method, Chauvet criterion, Cochrane's test. Then challenges of outlier detection. There are so many challenges. I just pinpoint some of the researchers identify the challenges. Then modeling normal objects and outliers effectively. Outlier detection quality highly depends on modeling of normal, is non-outlier objects and outliers. Application specific outlier detection, technically choosing the similarity distance measure and the relationship model to describe data objects is critical in outlier detection. Unfortunately, such choices are often application dependent. Different applications may have very different requirements. Handling noise in outlier detection. In most of the computer science, people are using these type of outliers. As mentioned earlier, outliers are different from noise. As for the statistician point of view, we discuss outliers are different from noise. In some of the computer science scientists are using outliers as the other name is called noise. It is also well known that the quality of real data sets tends to be poor. Noise often unavoidable exists in data collected in many applications. Understandably, in some application scenario, a user may want to not only detect outliers, but also understand why the detected objects are outliers. There are different categories of outlier detections. I just some of the researchers are using this kind of. There are many outlier detection methods in the literature and in practice. Here we present two orthogonal ways to categorize outlier detection. Outlier detection is one is called the superposition method, another one is statistical method. The superposition method is a semi-superposition method or unsupervised method. Statistical methods is either proximity based method or clustering based methods. Then superposition methods, modeling outlier detection as classification problem, samples examined by domain experts for training and testing. Methods for learning a classifier for outlier detections effectively. Model normal objects and report those not matching the model as outliers, or model outliers and treat those not matching the model as normal. There are some challenges. Imbalanced classes, that is outliers are rare. Boost the outlier class and make up some artificial outliers. Catch as many outliers as possible. Recall is more important than accuracy, that is not mislabeling normal objects as outliers. Then semi-supervised method situation. In many applications, the number of labeled data is often small. Labels could be on outliers only. Normal objects only or both. Semi-supervised outliers detection regarded as application of semi-supervised learning. In some labeled normal objects are available. Use labeled examples and approximately unlabeled objects to train a model for normal objects. If only some labeled objects and some labeled outliers are available, a small number of labeled outliers may not cover the possible outliers well. To improve the quality of outlier detection, one can get help from models from normal objects learned from unsupervised methods. Then unsupervised method assume that normal objects are somewhat clustered into multiple groups, each having some distinct features. An outlier is expected to be far away from any group of normal objects. Weaknesses. Cannot detect the collective outlier effectively. Normal objects may not share any strong patterns, but the collective outliers may share high similarity in small areas. Example, in some institution or virus detections, normal activities are diverse. Unsupervised methods may have a high false positive rate, but still miss many real outliers. In present pandemic situations are using these kind of situations. Supervised methods can be more effective. Example, identify attacking some key resources. Many clustering methods can be adapted for unsupervised methods. Find the clusters than outliers, not belonging to any clusters. Problem one, hard to distinguish noise from outliers. Problem two, costly since first cluster, but for less outliers than normal objects. Never method tackle outliers directly. Then statistical approach. A statistical approach method for clustering, statistical methods for outlier detection make assumption about data normality. They assume that normal objects in a data sets are generated by a stochastic process or random process, a generated model. Consequently, normal objects occurs in regions of high probability for the stochastic model, and objects in regions of low probability are outliers. In statistical approach, there are two major approaches, two major classifications. One is parametric method and one is a non-parametric method. In parametric method, there are three different classifications: reduction of univariate outlier using normal distributions and reduction of multivariate outliers using mixture of parametric distributions. These are will be under classification of parametric methods. In non-parametric methods, outlier reduction using histograms. Then parametric methods. The parametric method assumes that a normal data objects that are generated by a parametric distribution with the parameter theta. The probability density function of the parametric distribution f of x comma theta is the probability that objects x is generated by the distributions. The smaller this value, the more likely x is an outlier. Univariate outlier reduction based on normal distributions. Data involving only one attribute or variable are called univariate data. For simplicity, we often choose to assume the data are generated from normal distributions. We can learn the parameters of the normal distribution from the input data and identify the points with the low probability as outlier. Example, average temperature. There are 10 observations. A city's average temperature values in July in the last 10 days in values are setting under average temperature. You can use the maximum likelihood method to estimate the parameter mean and variance. Then for the above data, with the n equal to 10, we have mu equal to mu 28.361. Standard deviation equal to 1.99. It is called mu. The typographical error is called mu. Similarly, here standard error. Using the 3 sigma limit here, x minus mu divided by sigma, x is 24. You can take first sample 24. Mean 28.6 divided by standard is 1 by 2. This is equal to is less than or equal to -3. So 24 is an outlier since it lies between 3 sigma limits, which contains 92.7 data under the assumption of normal distributions. These are the simple examples. The next one is called a data involving 2 or more attributes of variables, multivariate data. Many univariate outlier reduction methods can be extended to handle multivariate data. And multivariate outlier reduction using Mahalanobis distance. For multivariate data sets, let O bar be the mean vector for an object. O is the data set. The Mahalanobis distance from O to O bar is the Mahalanobis distance MT O minus O comma O bar. Give me O minus O bar wrongly mistakenly. Where S is the covariance matrix, in Mahalanobis distance O comma O bar is the univariate variable, and this group test can be applied to this measure. In some of the researchers using this test under the multivariate data sets. Therefore, we can transform the multivariate outlier decision task as follows. There are following four decisions. Calculate the mean vector from the multivariate data sets for each object O. Calculate multivariate Mahalanobis distance O comma O bar. The Mahalanobis distance from O to O bar. Deduct outliers in the transformed univariate data sets. Mahalanobis distance O comma O bar given under all objects belongs to D. Then, if Mahalanobis distance O comma O bar is determined to be an outlier, then O is regarded as an outlier as well. Using mixed parametric distributions, if we assume that the data were generated by a normal distributions, this works well in many situations. However, this assumption may be overly simplified when the actual data distribution is complex. In such a cases, we instead assume that data were generated by a mixture of parametric distributions. Consider a data set in figure 5. There are two big clusters, C1 and C2. To assume that the data generated by a normal distribution would not work well here. The estimated mean is located between the two clusters and not inside any cluster. The C1, C2 cluster. The objects between the two clusters cannot be detected as outliers since they are close to the mean. Non-parametric method. In non-parametric method for outlier detection, the model of normal data is learned from the input data rather than assuming one clear. Non-parametric method often make fewer assumptions about the data and thus can be applicable in more scenarios. Clustering-based approaches. Clustering-based approaches, there are 4 classifications. Deducting outliers as an object that do not belong into any cluster. Clustering-based outlier reduction using distance to the closest cluster, intrusion reduction by clustering based outlier reduction, detecting outliers in small clusters. Then application of outlier reductions. The fraud reduction. Purchasing behavior of a credit card owner usually changes when the card is stolen. Abnormal buying pattern can catalyze credit card abuse. Medicine. Unusual symptoms or test results may indicate potential health problems of your patient. Suppose it's cancer or major disease comes under this purview. Whether a particular test results is abnormal may depend on the characteristics of the patients. For example, gender or age or some other criteria. Then public health issues. The occurrence of a particular disease, example, scattered across various hospitals of a city indicate problems with the corresponding vaccination program in that city. Whether an occurrence is abnormal depends on different aspects like frequency, spatial variation, etc. Nowadays, it is very apt example in pandemic situations. Then sports statistics. In many sports, various parameters are recorded for players in order to evaluate the player performance. Outstanding in a positive as well as negative sense. Player may be identified as having abnormal parameter values. Sometimes players show abnormal values only on a subset or a special combination of recorded parameters. Then detecting measurement error. Data derived from sensor, example in a given scientific experiment, may contain measurement error. Abnormal values could provide an indication of measurement error. Removing such errors can be important in other data mining and data analysis tasks. There are, as per the Hodge 2004, he pointed out some of the pictorial examples in fraud detection. Fraudulent application for credit cards. State benefits or fraudulent usage of credit cards or mobile phones. Then credit card fraud, an abnormally high purchase made on a credit card. Cyber intrusion, a web server involved in FTP traffic. Loan application processing, fraudulent applications or potential problematic customers. Then intrusion detections. Intrusion detections such as unauthorized access in computer networks. Intrusion or action that attempt to bypass security mechanism of computer systems. They are usually caused by attackers accessing the system from internet. Inside attackers, authorized user attempting to gain and misuse unauthorized privileges. The scanning activities. These are just look into this figure. The compromising the machine with the vulnerability in the second row, third system. These are the examples. Then satellite images analysis. Satellite image analysis, identification of novel features or misclassified features. You see, this comes under the category of outliers. Then fault diagnosis. Fault diagnosis processing, monitoring to default fault, for instance, in motor generators and pipelines. Then networking performance. Networking performance, monitoring the performance of computer networks, for example, to detect network bottlenecks. Then structural defect detections. Structural defect detections such as monitoring of manufacturing lines to detect fault production runs. For example, among these 10 VPSCs, in the second VPSC hose, pressure high, gas flow is low. These are all the indications. Then detecting novelties. Detecting novelties in images for robot or new taxes or surveillance systems. Then motion segmentation. Motion segmentation such as detection of the features of moving images, independently on the background. The time series monitoring. Time series monitoring of safety critical applications such as drilling or high-speed milling. Then medical conditions monitoring. Medical condition monitoring such as heart rate or heartbeat, etc.
Professor, can you make it 5 minutes, please? Because we have to stick to the schedule. Already we are. Thank you.
Thank you. I'm just giving some motivation for the young scholars. Detecting novelty in text for the piece. Then now my topic is comes under the high dimensional approaches. There are many real data sets are very high dimensional in some scenarios. Real data sets may contain hundreds or thousands of dimension with increasing dimensionality. Many of the conventional outlet detection methods do not work very effectively. This is an artifact of the well-known curse of dimensionality. In high dimensional space, the data becomes sparse, and the true outlets becomes masked by the noise effects of multiple irrelevant dimensions when analyzed in full dimensionality. The outlet detection for high dimensionality. These are all the challenges in high dimensionality data sets. Course of dimensionality, the relative contrast between distance decreases with the increasing dimensionality. Data is very sparse. Almost all points are outliers. Concept of neighborhood becomes meaningless. Some suggestions: use more robust distance functions and find 5 full dimensional outliers. There are some neighbor ranking based methods, subspace learning based methods, ensemble learning based methods. Then angle based outlier degree, grid based subspace outlet reductions, subspace outlet reduction. These are all some of the important points for the high dimensional data. The major challenges in research areas, particularly in computer science peoples and statistics, young researchers are concentrating these areas: machine learning, information theory, spectral theory, data mining, and that comes everything, and that comes to statistics. Then outlier detection technique, it is the major issues, identification and detection. There are application domains in fraud detection, intrusion detection, fault damage detection, crime investigation, counter terror, planning, medical informatics. These are all the applications domain. There are so many problems are characterized under different characters: nature of data, labels, outlier types, outputs, or under comes to the outlier detection techniques. These are all some of the references. Thank you. Please, those who are young researchers, interested scholars, please to do in this area. It's very interesting areas. Now, on behalf of organizers, it is really once again I record my thanks on behalf of my own and the department. In this department is developed in all well wishers, Professor KMP, Professor Suresh Chandra, Professor Global, Professor Jaya, and Professor Angopan. Whenever he visited India, he immediately comes to visit in this department. Professor Angopan and his team, and Ravanan, Kamalesh, Balu is working with us. Even though he is in Pittsburgh, he is always contacted with our scholars and the faculties. He motivated all the scholars. Professor Tangaraj is also my during 91. I think he only shaped my thesis because I'm a first student of Professor Sivasamy. Really, he only motivated to do research. The entire thesis, the entire contribution is under the completely changing Professor Tangaraj contribution. During the 1 week, he visited. He was at the time staying in Anand guest house. I just met Professor Tangaraj. He is completely my entire thesis during the 92. So in this occasion, I thank Professor Tangaraj. He is always with supporting all the research related activities. Thank you, Professor Tangaraj. Thank you, sir. Thank you all eminent scholars and young scholars. Please interact with the well-wishers of this statistics. Thank you.
Thank you, sir. Thank you for the overview of outlier detection. Very interesting. I don't think we have time for questions, but if there is any burning questions from someone else, can you please be brief and yeah, we can take one or two. Thank you.
Professor Andupayam.
Thank you, sir.
Shall I pose one question?
Sure, sir. Go on. Thank you, sir.
It's a great pleasure, sir. Question in English and answer in English, please.
No, this is regarding your Yendran picture. Right? There, you have shown the picture black sheep among the white sheep.
Yes.
Yes. Now my question is, there are cloning process.
Yes.
If there's a one white ship is a clone of the other, whether you will treat it as an outlier or inside the data. Number question. And number two, if you have a wolf among the flock of sheep, will you treat it as an outlier or not? You follow my question?
Yes, Professor. Yes, Professor. Thank you for giving me. This question is young researchers. Those who are working in computer science people will be very useful. But anyhow, I try to answer your query, Professor. The first thing is the problem of outlier is also somewhat it says as vague. Somewhat the identification is such a major issue. When you are thinking as it's outlier, then you are using the certain procedures available in literature.
Therefore, now my question leads to two things.
Yes.
Inclusive outlier and exclusive outlier. I don't know whether the concepts are available in literature. Inclusive outlier, I mean the clowning one. The exclusive outlier is the wolf among the flock of sheep or black sheep. I don't know whether such concepts are available in your outlier concept.
No, Professor,
Anyhow.
just to motivate the young scholar, Professor. Those who are working computer science, it is a really open problem.
Okay. Right. Now, in your MLE estimate slide, mu and sigma.
Yes.
Why you have put mu square?
Wrongly typed. Sorry, it is a new one. It is only new, Professor.
Where is that mu cap square comes?
No, sorry, Professor. It is only new. Wrongly.
Yeah, it can be corrected. Yes.
It's a type. I think it's a
The typo,
typing
sir.
error. Typing error.
Outlier. No, I mentioned
Outlier is squared.
it is wrongly.
Okay. So this is an excellent talk. I appreciate the speaker for his nice presentation. Thank you.
Thank you.
Thank you, Professor.
If there are no other questions, let's move on to the next session. Thank you.
Professor Gopal.
Oh, okay. So, okay, yeah. Yes, sir. Please go on, sir. Sorry, I didn't notice.
Yeah.
Yeah,
Gopal,
yeah.
sir.
Go on, sir.
Vanakkam,
வணக்கம்
vanakkam.
சார் வணக்கம்
அடுத்து வெளிநாட்டுல இருந்து வரவங்கள தான் நோட் பண்ணுவான் சார், உங்களெல்லாம் நோட் பண்ண மாட்டாங்க. கொஞ்சம் இதுன்னு
வெரி குட் சார்
சார் எங்க நோட் பண்ணுவோம்.
கண்டிப்பா இந்த மியூ ஸ்கொயர் எப்படி வந்ததுன்னா சிக்மா ஸ்கொயர்ல இருந்து வந்துருச்சு.
Speaker mentioned during his presentation, it's a typo error. So thank you, sir. Thank you. Really.
Thank you, sir. Thank you, sir.
Thank you. So let's move on to the next session. Thank you, sir. Thanks.
Thank you, Professor.
Please take over, Ramdurai or Suresh.
Sir, thank you very much, sir, for your nice motivational lecture to especially young researchers, sir. Thank you so much, sir, for having accepted our invitation and having delivered Professor K.N. Kunduswamy, sir, endowment lecture, sir. Thank you so much, sir. Thank you.
Professor Santamarai, thank you very much. Thank you, sir. Thank you.
Professor Santamarai, thank you very much.
Thank you.
கொஸ்டின் இல்ல, தப்பிச்சிங்க போங்க.
I would like to welcome Professor A. Loganathan, Professor, Department of Statistics, Manomuniyam Sundaranar University, to chair the Professor K.N. Venkatraman Endowment Lecture. I now request Dr. M. Ramadurai, co-convener of the conference, say a few words about this session.
Please, others, please mute your mic. Please. Hello, Harita, please mute your mic. Hello. Or someone mute her.
Technical, please.
super good.
Ramadhan,
is a good player.
Ramadhan, Ramadhan.
Sir, good morning, sir.
இல்ல டாக்டர் வெங்கட்ராமனை பத்தி யார் சொல்றா?
நான் தான் பேசுறேங்க சார்.
ஓகே ஓகே.
எஸ் சார், எஸ் சார், எஸ் சார்.
எனக்கு அந்த இது நானே சொல்லிடுவேன், பட் ஐ டோன்ட் ஹேவ் தட் மெட்டீரியல் நவ.
இப்ப உங்களுக்கு ஒரே நிமிஷம் அனுப்பிச்சுட்டுமா சார்? அப்படியே சார்
வாட்ஸ்அப்ல தேவைடா.
எஸ் சார், ஷூர் சார், ஷூர் சார்.
So I can start the talk because I have a meeting at 11:15. I don't have time. I can start talk.
Professor Sangaran, good morning, sir. Sir, Professor Sangaran, good morning.
Good morning. Good morning. Good morning.
Good morning, sir.
Good morning. Good morning.
Good morning.
Can I start my talk? Because
Yes,
I'm
yes.
short.
Just
Already
yes.
running light.
Certainly, there is an introduction to the endowment for a few minutes, then later on we will start.
Professor, sorry for the late, Professor, sorry, please.
Professor Ramadhan,
கிடைச்சிருச்சு ராமதரா, கிடைச்சிருச்சு. ஓகே.
Good morning to all, sir. Now I invite Professor and former HOD of Statistical Department, Professor G. Gopal, sir, to introduce about our Professor K.N. Venkatraman, sir, endowment lecture. Sir, please, sir.
Gopal, unmute. Professor Gopal, please unmute.
Yeah. Good morning to every one of you.
Professor Gopal, please unmute.
Yeah. Dr. K.N. Venkatraman was born in 1934 in Kuthanur, Nannilam Taluk of erstwhile Tanjavur district. He studied BA Honors from Trichy St. Joseph's College. Subsequently, he got his PhD in mathematics from Madras University under the guidance of Dr. D.V. Rajalakshmanan in time series analysis, and his examiner was M.S. Bartlett. And M.S. Bartlett, incidentally, is the guide of Rajalakshmanan. And Venkatraman contributed extensively to the Department of Statistics. And in 1975, he bifurcated Statistics Department from Economics Department and started a new department in the Madras University called the Statistics Department. During this period, he introduced the MSc Statistics course with rich mathematical content. And his teaching was unique. It is, he normally proves a theorem in one stroke. He will continue a theorem. In proving a theorem, he will find out a lot of new ideas, and the students will enjoy the new ideas, the new mathematical ideas Dr. K.N. Venkatraman normally introduces. And during his headship, the department got a lot of recognition. The FIP program started in this department, and many professors got their PhD in statistics in different subjects like time series, branching process, the city size distribution, all these areas. He contributed extensively in his research. And the probability, he emphasized more on real analysis, measure theory, probability theory, and he used to teach the statistical inference with the measure theory approach. That is what normally Venkatraman does in the classrooms. And he guided about 5 PhD students, and Venkatraman published several research papers. And the unique feature of his paper is the length of the paper. In one issue of the journal, the journal published only one paper in view of the length. And one issue occupied his paper. That is the unique feature of his research. And during his headship, many scholars got coveted positions in government and private sectors. And you must be knowing about Mr. Manikam, the chairman, Sakti Group, Pollachi Mahalingam's SARS group, and he got his PhD from this department. And similarly, many stalwarts like Parameswaran, MS Murthy, Parsardi, Bhushal occupied a powerful position in Punjab Nation. Ananda Lakshmi from the joint director, government of Tamil Nadu Statistics Department. Similarly, our Professor Loganathan also got his PhD, MSc Statistics from University Department. And he was lucky enough to have his lecture also. Palanichami, another person, Palanichami also learned a lot many things from K.N. Venkatraman. And see, God was so cruel to him. And at the age of 47, he passed away. At the premature age of 47 in 1982 December, he passed away, leaving his well-wishers and students in tears. And after that, the well-wishers prepared for his endowment lecture during the early 80s, and subsequently the first lecture of Dr. K.N. Venkatraman was delivered by an eminent professor, I don't know his name, under the headship of Dr. K. Suresh Chandra in the Department of Statistics, and subsequently it is going very well. And thanks for the department organizing these lectures. Thank you very much. Thank you very much.
Thank you, sir. Sir, thank you very much, sir, for having introduced our professor, K. Venkatraman, sir.
Okay.
Thank you, sir. Sir, I request Professor Loganathan, sir, to chair this session and introduce the speaker, Professor P.G. Sankaran, sir.
Sure. Good morning, sir. It's my pleasure to chair this session. This is on Professor K. Venkatraman endowment lecture session. Professor K. Venkatraman, about Professor K. Venkatraman, Professor Gopal has given a very good introduction. And to mention, Professor Gopal was also a student and a colleague of Professor K. Venkatraman. I knew many things about Professor K. Venkatraman, not only from the classroom, but also from the mouth of Professor Gopal when I was a student there. And sir, Professor Gopal, sir, I remember well that the first speaker of K. Venkatraman's endowment lecture is Professor J.V. Deshpande. Okay, right. Now, let me introduce our speaker. Professor P.G. Sankaran is the professor and pro vice chancellor of Cochin University of Science and Technology. He did his MSc and PhD. He got MSc and he was awarded MSc and PhD by Cochin University of Science and Technology. And the positions presently he is holding is a professor in the Department of Statistics. Formerly, he was a pro chancellor, pro vice chancellor, and head of the Department of the Statistics in Cochin University of Science and Technology. To his credit, he has published 4 books. Among them, one is a book published by Springer. It is co-authored by Professor N. Balakrishnan. He was the speaker for yesterday's first session, and he has published more than 150 papers in peer-reviewed journals of international review. And he has received the honors, particularly the Vice Class Fellowship of DST, Government of India. And he also got Young Researcher Award from International Indian Statistical Association. There are a lot many things to say about Professor P.G. Sankaran. Of course, due to the time constraint, let me continue with this. And let me invite Professor P.G. Sankaran to make his presentation. Professor P.G. Sankaran.
Okay. Thank you very much for your kind words. Good morning to all. Professor Gopal and others. At the outset, I thank Professor Sindhu Mall for giving an opportunity to talk on survival analysis as part of the endowment lecture of late Professor Venkataraman, who is a great statistician in the sense that who built one of the major departments in South India. Okay, so this is an honor to me. So I thank Department of Statistics, Madras University, for giving this opportunity. Okay, my title of the talk is proportional mean model for panel count data with multiple modes of recurrences. Is it visible?
No, sir. No, sir. Not visible.
Okay, 1 minute. 1 minute. Sharing. Share. Oh. Sharing. Is it visible now? Is
Visible,
it
sir.
Yes,
Yes,
sir.
yes.
Yes, sir.
Visible.
Yes.
Visible, okay. This is a joint work with one of my students. She's working in a college, proportional mean model for panel count data with multiple modes of failure. So what I'm going to do is I'm going to introduce the panel count data. What is the difference between the panel count data and other type of data in survival analysis, and then how to analyze such a data. And this particular talk, I'm going to concentrate on regression models for panel count data with the multiple modes of recurrence. This is the content introduction, the proportional mean model, asymptotic results, simulation study, data analysis, conclusion, and references. Just 1 minute. Oh. So in survival studies, we are aware that in certain cases, we may not be able to obtain complete information on the event of interest due to various reasons. The interest in the survival studies is the occurrence of some specific event. In certain cases, these events can occur repeatedly. For example, recurrence of hospitalization or recurrence of the certain type of diseases or recurrence of failure of certain automobiles, etc. If the subjects in the study are monitored continuously, this type of recurrence provides the information on the time of the recurrence of all events, and we obtain recurrent event data. We can refer the Cook and Lawless 2000 book, which is a collection of all basic concepts and related things on recurrent event data. However, in some cases, the study subjects can be examined only at certain time points as the continuous observation is too expensive or impossible. As a result, only the number of occurrence of the events between subsequent observation times are available, where the exact occurrence times of the events are not available. The data so obtained is called panel count data. So in the panel count data, we do not know the exact time of the occurrence of that particular event, but we observe the that kind of subject at regular intervals of time, so that the number of occurrences of the events between the subsequent observation times are available. So panel count data is also referred as the interval count data or interval censored recurrent event data. See Lawless and Sang 1988 and Carl and Lachin 1988. These two early references you can see. If each subject is observed only once, A special case of panel count data occurs, which is commonly referred as recurrent status data. That means if one patient is observed only once, then we have a special case of panel count data, that is the current status data. An extensive review of the panel count data is given in Sun and Sahu 2013, which is a good book on panel count data. So the standard method in the analysis of panel count data is focused on two functions. One is the mean function, that is expected number of occurrence of events up to a particular time, that is the mean function, or the rate function, that is the rate at which the event is occurred for each subject, that is the rate function. So an estimator for the mean function based on isotonic regression theory is developed by Sun and Kalfish, 1995. Under the assumption that the number of events on the recurrent events are non-homogeneous Poisson process, a non-parametric maximum likelihood estimator and a non-parametric maximum pseudo-likelihood estimator for the mean function has been proposed by Bellner and Sang 2000. Then some of the other references you can see in this book, in these papers. Sang, Jamshed in 2003, Su et al. 2013, Chio et al. 2018, and another reference by the same authors 2019. Just 1 minute. When the study subjects are exposed to recurrent events of several types, we observe the recurrence due to each possible mode or cause of recurrence at different observation times. I can give an example here. Consider the data obtained from skin cancer chemo prevention trial given in Sun and Sahu 2013. The cancer occurrence of 290 patients with a history of non-melanoma skin cancers are observed at different monitoring times. We are not observing continuously, we are observing at different monitoring times. The types of cancers are classified into basically two here: basal cell carcinoma and squamous cell carcinoma. And recurrences due to both the types of cancers at each monitoring time are observed for each subject. Covariate information on age, gender, number of prior tumors, and DFMO status is also observed for each individual. Accordingly, we can see this is the an extract of that data, panel count data. You have a patient ID 1. You have the covariate, that is gender, age, and the size. The other one is number of prior tumors. That is the other one. Then the observation number, you can see at a time 180 days, 180 days T number of days, that is 180 days, 350 days, 538 days, etc. The N1 due to basal carcinoma, N2 due to the other one, squamous carcinoma. You have the recurrences 0 up to 180 days. You do not find any recurrence due to that one. So you can see the data. N1 corresponding to the first course and N2 corresponding to the second course. T is the time at which the individuals are monitored. So these are the data. Then the question is, okay. Then, even though the panel count data was a topic of interest from last 2 decades, only a limited amount of literature is available on panel count data with multiple failure modes. Myself and Sridevi, we have developed an estimator for cause-specific mean function, which was appeared in Journal of Applied Statistics in 2020. And we also considered cause-specific rate functions of the underlying event process when subjects are exposed to more than one recurrence time. And both of these works considered data without covariate. So our objective here is to talk about the regression model of panel count data with the multiple failure mode, which is not considered yet. So we introduce a proportional mean model to estimate the regression parameters and baseline cumulative mean functions of panel count data, which is exposed to more than one mode of recurrences. This is the motivation of study. Now we basically present the basic concept, that is, consider a study consisting of n subject or n patients exposed to recurrence events due to different types, 1, 2, 3 types. Assume that event process is observed on a sequence of random monitoring times. We do not have exact time of recurrences. Consequently, the counts of the event recurrence due to each mode in between the observation times are available. The exact recurrence times remain unknown. We define a counting process, NJT, where NJT denotes the number of recurrences of the event due to cause J corresponding to the corresponding to the time T. Expected value of NJT is capital lambda JT, denote the expected number of cumulative events due to cause J up to time T. This is the function which we are interested. The function lambda JT is the mean function of the counting process corresponding to the cause J. Therefore, this is referred as cause specific mean function. Assume that corresponding to each subject, we observed a vector of covariate denoted by Z. So our interest is to study expectation of NJT given Z, that is capital lambda J T given Z, the expected number of cumulative events due to cause J up to time T conditionally on the covariate Z. So our objective is to find out how what is the relationship between this Z, the covariate Z, and the recurrence time. That is our interest. To estimate the effect of covariate Z on recurrence time T, we propose the model given in equation number 1, that is the proportional mean model. Capital lambda J T given Z can be written as a baseline mean function multiplied by covariate factor, where beta J is the regression parameter which we have to estimate. And similarly, we do not know lambda naught JT, we have to estimate the lambda naught JT also. When k equal to 1, this reduces to the proportional mean model referred in the book by Sun and V 2000, or the paper in Sang 2002 and Weller and Sang 2007. Now, coming to the data structure, let capital M be the integer value random variable denoting the number of observation time which may be different for each individual. We do not know what will be the number of observation time corresponding to each individual, which can be also considered as random. Tm is the random quantity. So Tmp be the set of observation times, that is M equal to 1, 2, 3. For example, for some individual we are observing 5 times, for certain individual we are observing 7 times. So the number of observation times will be different. Assume that NJT and MT are independent, and let MP denote the number of recurrences of the event due to cause J up to monitoring time TMP, not M, TMP, where P equal to 1, 2, 3, etc. M, J equal to 1, 2, 3, etc. K, and N MPJ is NJ TMP. For each subject, we observe a covariate vector Z. Now we have an independent and identically distributed copies of the n subjects. That is, each subject we observe these quantities. So the observed data will be small mi, which corresponds to capital M, TMIP, that is the time at which the observation happens. Then NMIP, that is the number of recurrences corresponding to each cause. 1 means first cause, 2 means second cause, etc. K means kth cause, and Zia is the value of the covariate corresponding to ith subject. So this is a data structure. So the regression model of analysis of panel count data based on maximum likelihood method with a single failure mode was explored by Sang 2002 and Wellner. Sridevi and Shankaran studied panel count data with multiple modes of failure recurrence and developed a pseudo likelihood equation for the observed data and derived an isotonic regression estimator for cause-specific mean function. They constructed a pseudo likelihood function for the observed data by assuming that successive counts of the recurrence events NJT are independent random variables. So we extend the derivation to pseudo likelihood function into a scenario with the covariate. So we consider the this equation 2 based on the assumption that this NJT is a non-homogeneous Poisson process with the conditional mean function. Thus, the mean function, as mentioned earlier, capital lambda naught j into e to the power of beta jd raised to m. So the one minus is missing. Exponential of minus lambda naught j e to the power of beta j raised to divided by m factorial. This is the Poisson main function, Poisson density or Poisson distribution. When the k greater than 1, the modes of recurrence are independent, the pseudo likelihood log likelihood function can be written in equation 3, where equation NJD, this will be this form. How to obtain this is what you consider equation 2, then corresponding to each cause you have product j equal to 1 to k, and for each subject you have I equal to 1 to n. So then that will reduce us to the equation 3 with the log likelihood function corresponding to jth cause will be given in equation 4. Simple analysis. Okay, so this is, so basically we use the Poisson distribution and take the product for corresponding to each subject, then corresponding to each cause, then take a log, and those product can be converted into sum, so that will reduce us to this equation 4 and 3. Okay. Now I am not going to explain the details on this computing, but briefly we give some idea. We assume that given the covariate vector Z, the distributions of T and M are independent of beta j and capital lambda naught j. We maximize the log pseudo likelihood function given in equation 4 to obtain the estimators of beta j and capital lambda. So we try to maximize this and find out the value of beta j and lambda naught j. Then for this, we consider the set indicator function and S1 less than S2 less than SR be the distinct ordered observation times in this set. So what we do is we consider the collection of all observation times, that is corresponding to each individual we have observation time. We consider the collection of these observation times, then we order these observation times. That is what S1, S2, etc. SR. Then we define this quantity, particularly define the number of observations made at SQ due to cos j, that is equation 5. Then take the average of those quantities, that is the mean value of the recurrence made at SQ, that is the QJ. Then then we have some quantities VB and W, so that what will happen is the earlier equation 4 can be converted into the form given in 9. So that's just a transformation of 4 by using these quantities. So that is it. Now maximization of this 9 will provide the value of beta and capital lambda naught j. So the equation 9 of then the estimator can be obtained by maximizing the quantity, which will give in equation 10 now. So to provide a maximum likelihood estimator or pseudo maximum likelihood estimator using this optimization method, we first choose initial values and these initial values, and then you find out the initial value of beta j, and then evaluate the value of capital lambda naught j. That will be given the estimate of lambda naught j hat. Then substitute this lambda naught j, then find out the value of beta j, and this process is repeated until the convergence attained. So this is the process. So this is repeat the step. What I am saying, giving an initial value, then find out the estimator of lambda naught j, then choosing this lambda naught j and then estimate the beta j, and the process is continued until the convergence occurred. This is I'm not going to discuss the details of this. We can prove the consistency of this and the rate of convergence and asymptotic normality of this beta j hat, all those things are. Now coming to the simulation study, for the here what our objective is to assess the efficiency of the proposed method. So we carry out a simulation study to assess the performance of the proposed estimation procedure in finite sample. We consider two competing risks. Then we generate the panel count data, that is MI, we have to generate MI, T, MIP, and ZI. Then we have two covariate in this case, ZI, ZI1, ZI2, two covariate, mutually they are independent. Then for each covariate ZI is generated from Bernoulli distribution. The first covariate is generated from Bernoulli distribution with the probability of success, that is 0.5. The second one is generated from normal distribution. So one is a continuous covariate, one is a discrete covariate. Then the number of observation times MI is generated from uniform distribution. So the maximum number of observation for each individual is restricted up to 5. So because of the constraint in the uniform distribution. Then discrete observation times TIMP are generated using above two mentioned two gap times. The gap times are generated also from uniform distribution. Then once the observation times are generated, number of recurrences are generated from bivariate Poisson process. So since you have two competing causes, you consider a bivariate Poisson process and generate number of observation times from this bivariate Poisson process. Then beta 1 and beta 2 are the regression parameters corresponding to two causes, and here rho is the covariance between the number of recurrences due to two causes. Then we consider the baseline hazard as T and 2T, and the sample size is taken as 50, 100, and 200, and process is repeated 10,000 times, and we calculate absolute bias and MSE of the estimates, and various parameter values of beta 1 and beta 2 are considered. Since most of the results are similar, we present some combination of beta 1 and beta 2 in tables. So to obtain the convergence, we choose epsilon is a very, very small quantity, that is 10 raised to minus 5. So these are the results corresponding to simulation study, that is absolute bias and MSE of the estimators of the regression coefficient for various values of beta are given with the lambda naught 1, T, lambda naught 2. You can see that this the bias corresponding to beta 1, this is the bias corresponding to beta 2, and these are when sample size increases, naturally the bias and MSE decreases. Okay. Then this is another combination with okay, absolute bias and MSE of the estimators. From the simulation series, we observe that the absolute bias and MSE of the estimator regression coefficient approaches negligible as sample size increases. This ensures that proposed estimators are unbiased with the nominal variance. Minimum value of the bias and MSE are obtained when the true baseline function takes the form lambda naught j equal to t for both j equal to 1 and 2. One can consider other forms for baseline hazard also. This is one lambda naught j equal to t. You can consider other combinations also. Data analysis. Now the proposed estimation procedure is applied to the real data on skin cancer chemo prevention trial discussed in introduction. The primary objective of the study was to evaluate the effectiveness of drug DFMO, that is in reducing new skin cancers in a population with history of non-melanoma skin cancers, basal skin cancer, carcinoma and squamous cell carcinoma, 2 types of skin cancers. The patients were randomly assigned into 2 groups, a treatment group with the oral DFMO and placebo group. Data consists of, as mentioned earlier, 290 patients with a history of non-melanoma skin cancers who were supposed to be observed every 6 months. However, the real observation and follow-up times differ from patient to patient. The data include number of recurrences of 2 types of recurrence events, BC and SC. We treat these 2 types of cancers as 2 modes of recurrence following Sridevi and Shankaran 2020. In the data set, the number of observation on an individual varies from 1 to 7 and time of observation varies from 12 days to 1766 days. For each individual, we have information on age, that is a covariate, gender, and DFMO status, number of prime tumors. We consider all 290 patients in our analysis, which include 170 males and 160 females. To obtain more explicit conclusion, we analyze the data on males and females separately by taking covariate information on DFMO status and number of prior tumors. Out of 290 patients, 147 were assigned to placebo group and remaining 147 were treated with oral DFMO. Number of prior tumors varies from 1 to 35. The estimate of the regression parameter corresponding to with the corresponding standard errors for males and females are given in these tables. Corresponding to males, you have this, and corresponding to female, this. One can easily see that these are the significant which can easily obtained from the p-value. Then the thing is that some of the cases, these regression coefficients are negative. And for example, BC, basal carcinoma, covariate DFMO has negative coefficient for both males and female. But for SC, the one is DFMO is negative for males, but the other one is positive. Okay, so this is it. So the tables are 4 and 5. We can see that modes of cancer occurrences, BC and SC, affect males and females in different ways. Regression estimated for number of prior tumors is greater than 0, both males and females, and for both modes, which implies that as the number of prior tumors increases, hazard rate on the recurrence rate increases always. Since the hazard ratio is less than unity, we can see that the drug DFMO decrease assess the hazard rate of more males with both BC and SC, and for females with BC. So this case. One is positive, DFMO is positive, that's the reason. The baseline cause-specific cumulative mean function for males and females are plotted in figures 1 and 2. The solid line represents the baseline cumulative mean function corresponding to BC, and the other one corresponding to SH. So this is for males. We can see that after 1800, it will cross the solid line, that is SC is dominating much in comparison with the BC in the case of males. But in the case of females, you can see that this BC is always dominating, and C has less rate of or less number of cumulative mean functions. So this is what this is. If you consider this and this. From the plots of baseline cumulative mean function, we can see that recurrence rate of BC is higher in males than the recurrence rate of SC up to 1,800 days. And from that point, recurrence rate of SC crosses that of BC, and while for female, recurrence rate of SC is always lower than that of BC. The plots also show that the difference in recurrence patterns of events due to BC and SC for females and females. One value can see that the values corresponding to 500 for SC and for males and females. Lower value for males and slightly upper value for females corresponding to 500. So the panel count data with the multiple modes of failure often arise in follow-up studies that consider recurrent events exposed to multiple models. We proposed a new proportional mean model for the analysis of panel count data with the multiple modes of recurrences. Estimates of regression parameters at baseline cumulative mean function due to each recurrence mode are derived. A simple iterative procedure is developed for the estimation of parameter. The finite sample properties of the estimators in terms of bias and MSE has been assessed through a simulation study. A real data set on skin cancer chemo prevention trial is analyzed using the proposal procedure. What are the future goals in this direction? The estimation procedure we developed in this article concerns the pseudo likelihood of function of the panel count data. A maximal likelihood estimators in this situation can be developed by extending the result in Wellner and Sang 2010, which involves a more complex iterative procedure. Another possible approach is the estimating equation approach, which can also used for estimating the regression parameter analysis of panel count data with the multiple recurrence of modes. And in many situations, rate functions of the underlying recurrent event process are of importance than the main function. So the rate at which the recurrence occurs is more important than the mean function if you consider specific time points. So one can consider the analysis of panel count data with the rate functions. So cost-specific rate function developed by Shankaran et al. 2021 can be used to study panel count data when subjects are exposed to multiple recurrences. Another important area where we can study is the mixture of panel count data and recurrent event data. There are a lot of recent work in literature where some period of time or the certain duration of time, we can observe the individuals completely, and after a certain duration of time, you cannot observe the individuals completely. You have some discrete time point where we can monitor the individual. So this type of analysis is called mixture of panel count and recurrent event data. So there are a lot of works in recent days on this. So the analysis of such data in the presence of multiple modes is an area which has to be explored. So references, these are the major references. For the preliminaries, one can refer to the book by Sun and Sahu 2013, Statistical Analysis of Panel Count Data. It's a book by, and other ideas, you can refer this paper by non-parametric inference for panel count data with the competency. We have also published a paper in JISA, Journal of Indian Statistical Association, in last year, December, which is the testing problem, testing how to test or compare the different specific mean functions. That is the testing problem. So these are some of the area. Okay, I once again thank you for all for giving this opportunity and for patient hearing. Thank you very much. You can ask any questions or you can raise any comments. Please do.
Thank you, Dr. Sankaran, for presenting the nice work on proportional mean model for panel count data. And you have described the simulation studies you carried out, and you substantiated with a real life data analysis. And you have also showed the future, the possibilities for the extension of the future work in the same area. Now the session is open for comments and discussions. Questions?
Sir, shall I ask?
Oh, please.
Sir, it's a very nice lecture, sir. My doubt is regarding your covariates. Normally, in case of panel data, if you have time invariant covariates like gender, it will pose certain problems when we use in the classical setup I am talking about with respect to if you are using difference in different method or something like fixed model or random effect models. Do you face any such difficulties, or did you differentiate between time invariant covariates and the time variant covariates in this particular model, particularly with respect to the beta estimation?
That's a good question. The one thing we must remember in this context is we are not observing the exact time of recurrence or exact lifetime or whatever we do this. What we do is what we are going to do is we have to get the information on exact lifetime based on the monitoring time. Okay. We have the monitoring time, that is the time at which we are observing the subjects. We do not know the exact time of occurrences or exact time of failures of these individuals or subjects. So in this case, usually we do not consider a time dependent covariate. But there are some work on this case because exact time of, otherwise, if you consider usual survival analysis, for example, Cox regression model and other thing, where the lifetime is measured with the censoring, with a certain type of censoring measured, you can have that time dependent covariate usually. But in this case, we do not have information about the time at which the event occurrence. So we have an additional variable. The T here is not the lifetime. T here is the additional variable, that is the monitoring time. So one can consider, as you mentioned, one can consider analysis by what we do is how to affect this Z on monitoring time. And the relationship of Z, the covariate on monitoring time. So there are certain work which is already published in that book, Sun and Sahu book, without committing risk. Okay, but we can extend those work into committing risk setup by considering the effect of covariate on the monitoring time.
Thank you, Professor. Thanks for the clarification.
Comments, Professor Suresh Chandra and Professor Venkatesan, they were also present. Sir.
Sir. Hello.
Dr. Lango.
Yeah, Professor Lango. Sir, good evening. Sir, respected sir, respected speaker, I really appreciate the presentation, sir. Sir, I have one small suggestion and a small doubt, sir. Sir, usually the Koch proportional hazard model, there are a lot of work is done on both the panel data, current data, time to event data. For your presentation, will it the work the same type of estimation procedure to be adopted for these methods also, sir?
No. The panel count data, that is what I mentioned. That book, it's a about 400-page book. That book considered the different types of analysis of panel count data. Okay. They have considered parametric model and non-parametric analysis and semi-parametric models also. What we here considered is, we considered the panel count data with the multiple modes of recurrences, like committing risk data. So this work has been started by us, myself and Sridevi, and the first one without covariate was published in Journal of Applied Statistics in 2020. And subsequent work was published in Journal of Indian Statistical Association, where we compare basically a testing problem, comparison of co-specific mean functions.
Yes,
okay, yes. Here actually the quantity of interest is mean function, that is expected number of events occurring up to a time t. That is the mean function. But in usual survival analysis, we are interested on hazard rate model, the variation of hazard rate model, that is the Cox hazard rate or accelerated failure time model or additive hazard model or proportional odds model, those things are. Here we are interested on mean model, that is here the one which I discussed here is proportional mean model under different cause of occurrences. That is
Anyhow, thank you, Sankaran, for your wonderful lecture. Our department really enjoying your presentation. Thank you very much, Sankaran.
Okay, well, once again, thank you, Department of Statistics, Madras University, and thank you, Professor Suresh Chandra. After a long time, we are seeing. Thank you very much.
Are there any other questions?
Thank you, Logu. Thank you.
Thank you.
Well, Dr. Sankaran, just I have only one doubt regarding the simulation studies. You generated covariates through the two Zs. One is Zi1, another one is Zi2. Zi1, you generated values from the Bernoulli. Probably maybe that the panel data regarding the gender. The other one generated from the normal distribution. Of course, from your slides, I understand that the another covariate which is hidden is probably age. Am I right?
Yeah. What in the simulation study we have considered.
You generated Zi2 values from normal distribution.
Yeah.
May I know what is the data for which you generated used normal distribution for generation?
No, this is a
if it is the age.
Not age. I have not considered age. Two covariate. Normal distribution means we can use covariate which can take real value also. Some of the cases that can happen in general, but we consider one continuous covariate and one discrete covariate. Okay. Okay.
Oh, you did not mean that is the age.
No. The other one is not just one discrete covariate and one continuous covariate. That's all. But in data analysis, we have covariate. One is age. One is type of number of tumors. The other one is DFMO status. Three covariate.
Well, thank you, Dr. Sankaran, for making a nice presentation and for your interactions. Now I hand over the session to the organizers, and I take this opportunity to thank the organizers for inviting me to chair this session. Thank you.
Thank you very much.
Thank you.
Sorry, I have a meeting at 11:20. Okay, I am moving. Okay, thank you.
Thank you, Professor P.G. Sankaran, sir, for having accepted our invitation and having delivered this lecture, sir. Thank you so much, sir, on behalf of the organizing committee, sir. Thank you very much.
Thank you, Dr. Suresh and Dr. Sindhumal. Thank you.
Yes, sir. And thank you so much, sir. Thank you so much, sir. Now, it is the duty of the organizing committee to thank a respected professor and the distinguished alumni of this department, Professor A. Loganathan, sir, for having chaired this Professor K. Venkataraman, sir's endowment lecture, and his interesting yesterday's lecture, in spite of his busy academic schedule. Thank you so much, Professor Loganathan, sir. Thank you so much, sir.
Thank you. It's my duty.
Yes, sir. No, sir, it is our duty also, please, sir. Then our humble thanks to our senior professors and former HODs, respected Professor K. Suresh Chandra, sir, and Professor G. Gopal, sir, for having given us the valid information about the most respected Professor K. Venkataraman, sir's information. Thank you so much, sir, Professor K. sir and Professor Gopal, sir. And our humble thanks to respected Professor G. Gopal, sir, former professor and head of the department, and my own Dr. Guru, for having introduced Professor K.N. Venkataraman, sir. Thank you so much, sir.
I would like to welcome Professor V. Tangraj, former Director, Ramanujam Institute of Advanced Study in Mathematics, former Director, IDE, former Controller of Examinations, University of Madras, to chair the Professor S. P. Rajagopalan Endowment Lecture. I now request Dr. S. Suresh, the Conference Secretary for ICASMA 2022, to introduce Professor V. Tangraj.
It's a very good morning to all. So Professor V. Tangaraj, former Director and Head, Ramanujan Institute for Advanced Studies in Mathematics. Sir has completed his MSc and PhD in Mathematics at Annamalai University. After that, Sir started his career as a lecturer in Regional Engineering College, Tiruchirappalli in the year 1983. In the year 1985 to 2012, Sir was working as a lecturer, reader, professor, and Director and Head in Department of Mathematics, Ramanujan Institute for Advanced Studies in Mathematics, University of Madras. His contribution to University of Madras as a teacher, researcher, and administrator is a large and really appreciable. And Sir has published more than 50 research articles in international and national level journal. Sir produced more than 10 PhD scholars. Sir was a member of Tamil Nadu book writing team, 11th and 12th standard. And Sir also worked as a chairman, Integrated Board of Studies in Mathematics, Tamil Nadu State Council for Higher Education, UG and PG in Mathematics. With this brief introduction, I request to Professor chair the session. Thank you, sir. Sir.
அவரோட மைக் மியூட் ஆயிருக்கு.
Yes, sir. We will.
Unmute பண்ணுங்க.
Sir.
Professor Tangraj sir, please come close to the mic.
Sir. Sir, Professor Tangraj sir, sir. Sir.
Sir.
Please start the session. You please unmute.
Professor Tangraj sir, mic mute ஆயிருக்கு.
Yes, yes.
The VT is not audible.
சார் மைக் பக்கத்துல இருந்து பேசுங்க சார்.
சுரேஷ் சார் கிட்ட சொல்லுங்க.
போன் பண்றேன் சார்.
இப்ப கேக்குதா?
கேக்குது சார்.
கேக்குதுல்ல? Okay, okay.
Thank you.
Are you hearing me?
Yes sir.
Okay, fine.
இதெல்லாம் வந்து அவர் சொல்லணும்.
Okay. I think very good morning to one and all. It is a great pleasure to participate in this international conference, and also I thank the organizers for giving me an opportunity to chair one session in the name of Professor Rajagopalan Endowment Lecture. Anybody is going to introduce about this Rajagopalan Endowment Lecture?
Sir, already done, sir.
Sir, already completed.
Already done.
Yes, sir.
Shall we go straight to the talk?
Yes, sir.
Already it is too late. Okay.
Sir.
Now, under this Professor Rajagopalan Endowment Lecture, we have two speakers, eminent speakers, Professor Martin Luther William, and one more speaker. Now, regarding myself, I was working in the Ramanujan Institute for Advanced Study in Mathematics. That was my home, but my playground is Department of Statistics. I always in the Department of Statistics rather than in the Ramanujan Institute. Therefore, I consider this department as my playground to play around on probability and stochastic models. Okay, with this few things, Professor Martin Luther William has got undergraduate and postgraduate in statistics, also MPhil and PhD statistics. I think both are from University of Madras. He has held various positions, especially in faculty advisor outreach, and he was also the dean of students. His area of interest is estimating functions and prediction, and he has published more than 20 research publications. With this few introduction, I call upon Dr. Professor Martin Luther William to present his talk.
Good morning.
Good morning, sir.
Good morning, sir.
Am I audible? Am I audible?
Yes,
Yes, sir. Yes, sir.
Yeah, good morning, and thank the Lord Almighty, and good morning, sir, Dr. Thangaraj, sir. Thank you very much for introducing me to the audience, and it is nice to touch base with you after so many years. I think it might be about 20 years, I don't remember. After seeing you, I think long time since we met in person. Even today, of course, not in person, but at least we are able to meet virtually. Thank you very much, sir, for your presence here. And let me thank Dr. Sindhumol and her team, Dr. Ramudurai, Dr. Suresh, for considering me as a qualified person to talk in this August conference. So let me thank the organizers from the bottom of my heart. Indeed, Professor Rajagopalan is a person whom I listened to again long back. I think probably sometime in the 1980s, if I am correct. I used to attend a few lectures that he gave in the university. And after that, I think only now I'm again coming into close, a sort of relationship with Professor Rajagopalan. I think it's a great honor. I deem it as a great honor to give this invited talk as a part of Professor Rajagopalan endowment lecture. So thank you, organizers, for this opportunity to me. I think straight away I shall go to the topic. If you want time, I think better to start immediately. Actually, my areas of research originally was estimating functions and prediction in my PhD under the guidance of the former head of the Department of Statistics, Loyola College, Dr. Durirajan. And of course, now my areas include statistical inference, multivariate analysis, regression modeling, and so on. And as of now, the topic I'm going to present here is about multivariate analysis, the multivariate discriminant analysis, fully non-parametric, and a new paradigm for discriminant analysis. Discriminant analysis has been a long living topic. In fact, it has been in existence for many years, past about 70 years or more than that. But as of now, there are many new techniques that have overcome this multivariate discriminant analysis. Basically, multivariate discriminant analysis is meant for classifying an object, an individual, into one of two groups. Let me call them as a binary dependent variable. Usually we denote it as 1 and 0 or 1 and 2. Notation is not an issue. So two groups are there, and we want to allocate objects to classify, to predict the membership of an individual into group 1 or group 2. And for that, one classical technique is this discriminant analysis. Of course, there are various other techniques that have come now, logistic regression, probit models, classification trees, and random forests, and all those methods have come, sort of overtaking this discriminant analysis. But then this classical technique has its own beauty. It has been in existence for a long time, and we have just thought of reviving at least some new ideas and putting into some new ideas into this discriminant analysis field topic. So one of my PhD candidates worked on this area, and I'm just presenting one part of a we have worked along with one of my PhD candidates who worked on this discriminant analysis area. So let me present the screen. Share screen, okay. Okay, so it's not opening, just a minute.
Please click share screen.
Yeah. And sharing, is it visible?
Yes, sir.
Visible, sir.
Sir, is the screen visible?
Yes, sir. Yes, sir.
Yes, visible, sir.
Visible.
Oh,
Please click
okay,
down.
okay. Thank you. So this is discriminant. So discriminant analysis in a new paradigm. Of course, a non-parametric, totally non-parametric approach. And specifically, of course, a lot of work has been done in this along with my PhD student. But what I'm going to present here is only one particular algorithm and a variable selection, what popularly is called the forward model building process. So variable selection in discriminant model for optimal
Martin sir,
classification for
presentation
two
mode.
populations. So yeah, it's not visible, sir.
Sir, it's visible,
Visible
sir.
only.
Slide
You
is
can
not
make it
moving,
a
sir.
presentation mode.
Slide
Okay,
is
okay, yeah, I'm doing that, yeah.
Press F5 button to make it bigger.
Just a minute. Yeah.
Just press F5 button.
Yeah. Yeah, so is it okay, sir?
Oh.
Hello?
sir.
Sir, is it visible?
Yes, sir.
Please make it bigger.
Oh, okay. Yeah, I have put the full screen actually. Yeah. So variable selection in discriminant model for optimal classification to two populations, a non-parametric approach or what you call a distribution-free approach. The traditional discriminant analysis has several limitations. The restrictive assumptions that are there on the classical discriminant analysis are: one is a parametric approach where we can think about a joint distribution for the input variables, mainly multivariate normality. Of course, we can talk about any other joint distribution also, but basically it is multivariate normality. And there is a non-parametric approach where there is a strong condition or a strong requirement for equal variance covariance matrices in the two populations. And definitely verifying the equality of the variance covariance matrix under a non-parametric setting is not easily done. Because if it is normal, then we can go for an equality of variance covariance matrix test. But without any distributional assumption, there is no way to test this equality. And the second limitation is not really a limitation, but that is what is happening. The inclusion of variables is based on the comparison of means in the two populations, again, for which normality assumption is imposed. And the third one is the membership prediction or classification. It is based on the distance with the means of the discriminant in the two populations. So you measure the discriminant score for an individual. If that score is closer to the mean of the discriminant score in population A, then you classify that individual as a member of population
Sorry for the
A.
interruption. Speaker, please, your slides are not moving.
Yeah, I'm just talking about this current slide, sir. I'll move to the next one.
Okay.
So, based on the distance with the means of the determinant, the classification is done. And logically it is correct. So logically that there's nothing wrong in it, but it is not exactly optimal in practice. Now the existing issues, multivariate normality, that is one restriction, and the equality of the variance covariance matrix is not guaranteed in practice, even if you go for a non-parametric approach. So this is the current limitations in the existing discriminant analysis technique. Practical situations, there are two things that we do. One is you assume multivariate normality, verify the multivariate normality, and whether the variance covariance matrices are positive, and if it is tested positive, then go for the linear discriminant analysis. And suppose equality of variance covariance matrices is tested negative, then you go for the quadratic discriminant analysis. And there is one branch. The other branch is multivariate normality is not verified. So basically, there is no distribution. We are not able to know the distribution. So what people do is equality of variance covariance matrices is assumed, and equality of variance covariance, if it is assumed, we go for the classical linear discriminant analysis again. Whereas if the equality of variance covariance matrices is not to be assumed, and that is going to be a natural thing to do. Okay, so if we are not going to assume the equality of variance covariance matrices, then that is where we come to the currently proposed discriminant analysis. The motivation, there is no easy procedure for testing the equality of variance covariance matrices in a
Dear sir,
distribution-free setting.
sorry to interrupt you. We are still on first slide only. That's title slide. It's not moving at all. Probably you are on presentation mode, which is not shared.
One minute. Presentation. So actually, I have to click on share screen, right?
Yeah, yeah.
And that's where I clicked on, but then I don't know what is the problem.
I've already opened the PowerPoint, the background.
I am just clicking on the share screen option. Okay, that is right. Hello. Hello.
Yes.
Are you able to see the screen, sir?
Yes, sir. Yes, sir.
Okay, what should I do to present? I have to just share the screen. For presentation mode, what should I do?
Left side icons are there. You please click the desirable slide to show. On left side, there are slides. You please click them here. Or please click the top left button. Top from the beginning. Please click that.
Yeah.
Yeah, please, yes, please.
Okay.
Click the icon.
Yeah, now is it visible, sir? Yeah, I have clicked on it.
Icon.
Yeah, I have clicked on it, sir.
Okay, then you have to.
Alternatively, try the one at the bottom, sir.
No, don't worry. Please click the leftmost button, number 2. Now, slide 1 is.
So I click on the leftmost from beginning, right?
It is not seen now, please.
Final preparation.
Please press share screen.
Example from each file of the patient was next to me. Five by 6. Good. Very good.
Sir, please send your presentation to the organizers. They will screen it. Professor William, please send your presentation to the organizers.
Ramadurai. Ramadurai. Suresh. Ramadurai, Suresh.
Sir, yes, sir, yes, sir.
You get the PPT and then you run it. Get
Yes,
a
sir.
copy of the PPT.
Now, Professor has sent it to our mail ID, sir.
Yeah.
Sir.
Now you run it.
Okay,
See,
sir.
even before starting it, you have to start from the first one.
Sir, yes, sir, I am opening.
Sir, the message. And text message.
Please, sir,
Password.
கீழே வந்து ட்ரை ஆனது ஃபோன் நம்பர் 14
சொல்லுங்க சொல்லுங்க சார்.
சார் ஒரு நிமிஷம் சார் அப்படியே லைன்ல இருங்க சார் ப்ளீஸ்.
சொல்லுங்க சார்.
G731360
731360. சார் அனுப்பிச்சிட்டாங்களா?
நமஸ்கார்
சார்.
சார் இந்த மெயில ஓபன் பண்ணிட்டு இருக்கேன் சார், ஒரு நிமிஷம் சார். எஸ் 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 சார்.
இல்ல இல்ல சார்.
சார் மெயில் ஐடி என்ன அனுப்பிச்சிங்க? இன்னும் கிடைக்கல, எனக்கு வந்து சேரல சார். நான் ரீச்
MRT ஸ்டாட்டுக்கு அனுப்பிச்சேன் ஜிமெயிலுக்கு.
ICASMA காமிச்சிருக்கீங்களா சார்? எஸ் எஸ் சார், ஒரு நிமிஷம் சார், ஒரு நிமிஷம் சார், ஒரு நிமிஷம். சார் வந்துருச்சு சார். சார் உங்க பிபிடி வந்துருச்சு. இந்த இப்போ நாங்க அதை ப்ரெசென்ட் பண்றோம் சார். நாங்க சார் ஒரு நிமிஷம் சார். ப்ளீஸ் சார், ப்ளீஸ் சார். எஸ் சார், எஸ் சார். தேங்க்யூ சார், தேங்க்யூ. எஸ் சார், தேங்க்யூ சார். சார் இந்த ஒரே நிமிஷம் சார். அனைவரும் வித்தின் 1 minute உங்களுக்கு வந்துடும் சார். நீங்க ஸ்கிரீன்ல நீங்களே பார்த்துடலாம் சார். ஷேரிங்
ஸ்லைட்
சார், இஸ் இட் விசிபிள் சார்? Sir, is it visible?
Yeah, it is visible.
Yes. Okay, sir.
Okay,
Visible. Visible.
Move the slide. See that whether it is working or not. Go to the next slide.
Hello.
Sir, இது பண்ணிட்டேன் சார்.
Yeah, பார்க்க முடியுது. Yeah. Okay, no problem. Thank you.
Thank you, sir. Thank you, sir.
Yeah, you can move to the next slide, sir. It is visible to me. I hope it is visible to others also. Yeah.
It is visible to everyone.
Can you hear me?
யார் பேசுறதுங்க?
Dr. Williams, please unmute.
Unmute பண்ணிட்டேன். I have already unmuted.
Then you start talking.
அவரோட வால்யூம் கம்மியா இருக்கா?
Sir, I have already unmuted. Dr. Ramudurai, sir.
Please go ahead.
Okay. I have already unmuted it.
Sir, you are not audible, sir. Professor Martin, sir, you are not audible, sir.
I don't know why. I have already unmuted, sir.
He is audible.
I have already unmuted.
Yes, move to the next slide. Yeah, third slide.
Dr. Ramudurai, sir.
Yeah, now we can go ahead.
Dr. Ramudurai, நான் unmute பண்ணிட்டேங்க.
உங்க வாய்ஸ் ஆடிபிளா இல்ல.
You are unmuted and you are talking.
இங்க இருப்பாரு பாஷா. இங்க பாருங்க.
நாங்க பேசுறது உங்களுக்கு காதுல விழுதுங்களா சார்?
Yeah, I can hear.
Yes. Thank you.
Are you able to hear me now?
Yes.
It is audible.
Okay, it's audible now?
Yes,
audible.
Okay. Yeah, thank you. Okay, sir, sorry. I don't know why this happened. Okay, yeah. Okay, sir. So we go to the next slide. The next slide. Okay, so thank you, Dr. Ramudurai and team. The traditional discriminant analysis has several limitations, as I mentioned already. The restrictive assumptions on multivariate normality, or if you want to go for a non-parametric approach, there is a stringent requirement for equal variance covariance matrices, which cannot be easily verified. So that is one restriction and limitation. Variable inclusion is based on comparison of means only, again for which normality assumption is imposed. And then membership prediction is based on distance of the discriminant score with the discriminant mean in population 1 and population 2. And that is not logically correct, but that is not exactly optimal in real-time practice. Next slide, please. Sir, next slide, please. Okay, so the existing issues are the multivariate normality is an imposed restriction, and the equality of variance coded matrices is an imposed restriction. But then in practical situation, what happens? Multivariate normality is verified, and suppose it is verified, then you can go for a test for equality of the variance covariance matrices, because the test procedure is available to carry out the test. And If it is tested positive, then we go for the linear discriminant analysis. Whereas if the variance square matrices is not tested as acceptable, so if it is rejected, if it is tested negative, then we go for other approach where you have a quadratic discriminant analysis based on multivariate normal distribution. So this is okay if you assume multivariate normality or if you verify multivariate normality. But suppose multivariate normality is not verified, okay, it does not follow, then equality is assumed, the equality of variance square matrix is assumed, and the linear discriminant analysis is again followed. Whereas the real situation is that you cannot simply assume, because you cannot even test the equality, and therefore you are not assuming anything. So equality of variance square matrices is not assumed, and that is where we go for the currently proposed discriminant analysis approach. Next slide, please. So next slide. What is the motivation for this work? There is no easy procedure for testing the equality of variance covariance matrices in a non-parametric setting. In most applications, it is assumed, the equality is assumed, and the linear discriminant analysis is applied. The need to fill this gap and provide a discrimination cum classification procedure in a distribution-free, non-parametric setting without the condition of equal variance covariance matrices is the motivation for this work. The aim is to develop a theoretical framework first and a simple tool which leads to an efficient procedure which can be applied without the conditions that restrict the existing approach. Next slide. The objectives are to provide a theoretical framework for handling situations with unequal variance covariance matrices, to suggest a model performance measure for judging discriminant models, to present a variable selection algorithm for discriminating two populations, and an easy to apply procedure for classification of the objects. Next slide. The proposed approach is takes a different path from the existing approach, but we adhere to the fundamental spirit and the mathematical objective of classical discriminant analysis. So we stick to the same objective where we want to maximize the distance between the two populations. So that spirit we are adhering to. So the basic spirit and the mathematical objective of classical discriminant analysis is adhered to. And what we are going to do is to propose a model performance measure for the capacity of the model to maximally differentiate or discriminate the two populations. And we want to develop a variable selection algorithm to select the best variables in a forward one-by-one stepwise manner. And then we would like to provide a decision rule to identify the optimal cutoff point for maximizing the correct classifications. Because classification, what we do in the existing approach is we take the average of the score and we compare with the average score in population A and the average score in population B, and we see where it is close, and therefore we assign it to that population. Logically correct, but actually in practice you can see that it doesn't give you the most optimum classification percentages. So that is why we want to go for a different approach. Next slide, please. Thank you. Next slide. We consider two populations, pi1 and pi2, whose relative sizes or the proportions when combined are P1 and P2, what you call a prior information about the two populations. And let there be P observable random variables on the basis of which the discrimination procedure, the classification procedure is going to be done. And we assume that the means are, say, mean vectors, mu1 and mu2 in the two populations. Variance covariance matrices are not assumed to be equal, they are different. And we have the following general expression for the mean vector and the variance covariance matrix of the combined population, that is pi1 union pi2. So two populations taken together, because that is how we are going to get the data. The data is derived from the two populations put together, and therefore we are trying to look at the combined population and how the mean vector for this random vector x, and how the variance covariance matrix for this random vector x are going to be. And you can see that the prior information, the prior distribution of this pi1, pi2, that also plays a role in the overall mean vector and the overall variance covariance matrix of the combined population. So these expressions, they are derived. Next slide, please. Next slide, please. Now let us consider any linear combination of the xi's. Let me call it as L transpose x, where L is a column vector of constants. We can easily see what will be the means of y in the two populations. It will be L transpose mu1 and L transpose mu2 in the two populations. And in the combined population, it will be given by P1 into L transpose mu1 plus P2 into L transpose mu2. And the variance covariance, the variance of y is a scalar random variable. Please note that the variance of y in the combined population is given by L transpose sigma L, where sigma happens to be the combined variance covariance matrix, the variance covariance matrix of the combined population. Next slide, please. The linear combination which maximizes the squared distance between mu1y and mu2y relative to the variability in y helps in discriminating the two groups in the most optimal manner. So that is the very basic premise on which we start the work, and that is the basic principle of classical linear discriminant analysis also. The distance in the classical Fisher's linear discriminant analysis, the distance was measured relative to the common variability in y in the two populations, because common in the sense that in both populations the variance covariance matrices are assumed to be equal, and therefore you get a common variability in y. Whereas here the objective is to develop the optimal discriminant function in the unequal variance covariance matrices context. And because we have to compute distances between objects that belong to either of the two populations, so both together, there may be one individual from one population and one from another, and therefore we have to measure the distance between two individuals that belong to either of the two populations, and therefore the distance measurement will be more meaningful if it is measured relative to the overall variability of the linear combination y in the combined population instead of relative to the common variability. So common variability is not what we are talking about. We are talking about the overall variability that is there in the random variable y in the combined population. The distance maximizing linear combination of the xi's is known as the optimum discriminant function based on the random vector x. Let us call it x-based optimal discriminant, because x can vary, we can reduce x, we can add more variables into x, and therefore let me call it as x-based optimal discriminant. Next slide. Now this is the mathematical part. The square distance, similar to the classical approach, where the principle is to maximize the square distance between the means relative to the variability. But here we talk about the overall variability in y in the combined population. And the red mark, so I have given in red font, mu1 minus mu2 transpose sigma inverse x, where sigma is not the common variance covariance matrix, but it is the combined variance covariance matrix of x, and that is the optimal x-based optimal discriminant function. Now the discriminant score can be computed for every individual that is available for you from both the population pi1 and pi2. Next slide. We introduce a model performance measure, which is going to be something new, of course, based on what we already existed in the historically in statistics, but we are trying to modify this and present it so that it can be applied to this context. In any practical situation, several variables are considered by investigators, but for the purpose of actual discrimination or a proper discrimination between the two groups and good classification, so that our classification is done in the most perfect way, may not be 100% correct, but we would like to get it in with the highest possible correct classifications. Then some variables may be irrelevant. So an investigator may include many variables, but some of them may be irrelevant, and therefore, what is the use of retaining such variables in the discriminant model? It is pertinent to build the optimal discriminant model with only a subset of the variables considered. So what are the most important variables? Only that needs to be considered, and some nuisance variables can be removed. Thus, a need to compare the optimal discriminant models built on different subsets of the variables arises. So therefore, we have to compare between different subset models, and hence a measure to compare the models becomes essential. The optimal discriminant function must be capable of maximally differentiating the two populations. This differentiation or discrimination is reflected in the modified two-sample one-sided Kolmogorov-Smirnov statistic, which measures the difference, actually the signed difference, between the reliability functions of the discriminant in the two populations. Conventionally, Kolmogorov-Smirnov statistic is meant to compare two distributions through the cumulative distribution functions, but here we talk in terms of the reliability functions because that gives you an interesting meaning to the performance measure that we are going to compute. Next slide, please. Next slide.
Williams,
now,
you can take 5 more minutes.
Okay, sir. I don't think I'll be able to complete the talk. Anyway,
so
this is the. Okay, sir. Yeah. So these are the subset models that we talk about, and the case modified case statistic. What we are proposing here, I have given that here. Next slide, please. Given two subvectors, say XS1 and XS2, the optimal XS1 based discriminant is said to be more efficient than the optimal XS2 based discriminant. So with respect to XS1, we get an optimal one. With respect to XS2, we get an optimal one. But among the two, which is the better one? So that is considered to be more efficient if the case for S1 is greater than the case for S2. And if at all there is a subset for which the case is the maximum among all possible subset models, then we call that as the most efficient discriminant. And we note that the article A is used instead of the while referring to most efficient discriminant because we do not rule out the possibility of more than one most efficient discriminant. Next slide. Obtaining a most efficient discriminant is computationally prohibitive when you have very large number of variables. For example, suppose there are 10 variables, then you will have to think about 2 power 10 minus 1, that is 1023 models to get the best subset model. And you all know that we always cannot do that, and therefore we go for one step-by-step approaches, forward method, backward method, the bidirectional method, and so on. And here what we are proposing to do in this talk, I'm talking about only the forward method, because getting the best subset running all the several models will not be an easy task, and therefore we go for the variable selection method. Next slide. Cut point. The ultimate objective of discriminant model is optimal classification. But for that, we need a cut point for the discriminant score. Now, the cut point will be the point where the Kolmogorov-Smirnov statistic is attained. In other words, suppose there is a Y0 for which R1 is Y0 minus R2 is Y0 is the maximum, then that Y0 becomes the cutoff point, because that is where you are able to maximally differentiate between the two populations. The interesting part of this approach is that the identification of the optimum cutoff point is integrated with the computation of the performance measure, namely the modified KS statistic. Next slide. Best subset model, as I already pointed out, it is not easy to take the entire collection of subsets and run so many models. It is not an easy task, and therefore we have to look for stepwise approaches. So this is what I mentioned here. We'll go to the next slide. Mainly, the idea is to avoid nuisance variables in the model. And this is also about this subset model, where we have to construct too many models if we want to really identify the best subset model. Next slide. Linear regression models, logistic regression models. There are various approaches where you go for forward, backward, and so on. In discriminant model also there is such approach available, but these approaches are either restricted by the equal variance square matrix assumption, or it is applicable to only parametric context, missing out on the real non-parametric paradigm of variable selection in discriminant model building. And that is what we are trying to do in this work. Next slide. The proposed algorithm evaluates each candidate input variable for its discriminating capacity in a sequential manner towards constructing the best discriminant function. Here we take a different path to variable selection in a forward stepwise manner. The algorithm proceeds by bringing one input variable at a time on the basis of maximal differentiation between the distributions of the discriminant score in the two populations as measured by our modified KS statistic used for comparison of two distributions. The exact stepwise procedure is described as follows. Next slide. Next slide. You can see in the very first step, we are choosing the one which has the topmost KS value. Next slide. In the subsequent steps, we do the same by adding one more variable at a time. Let me go to the application that would be more interesting. Next slide, please. Fatty liver disease, you know, it's a very dangerous disease. Of course, it is sometimes it is non-serious, but certain cases, in the case of alcoholic thing, there is a very risk involved. But here we are talking about non-alcoholic fatty liver disease. Even people who do not consume alcohol, they have this fatty liver disease because of various other factors. Let us look at how we can do a classification of people with the risk of this NAFLD, non-alcoholic fatty liver disease, versus the people who do not have the disease. Next slide. We can see that there are so many variables: age, triglyceride, the gamma glutamyl transferase GGT, height, weight. Next slide. BMI, waist circumference, and a fatty liver index, which is also a measure which is already available in the medical literature. So these are the variables that are considered for our discriminant analysis initially. All these variables may not be required, but then we would like to see how our model building goes. Next slide. Sample size was 80 and 80. There is a study group and a control group. We call it as 1 and 2. The prior information about the populations are important. Sometimes there may be no prior information, in which case we can assume that P1 and P2 are both equal to half. However, if prior information is available, it is always good to use. We proceed with two prior distributions, one with the equal prior, and one with P1 equal to 1 by 3 and P2 equal to 2 by 3. Next slide. So this is a single variable model. In the very first step, you can see that X5, that is weight, it has the highest KS value, and therefore weight is the first variable that enters into the model. Next slide. Now we are adding along with weight, that is X5, we are adding X1, we are adding X2, and so on. And we try to see which variable enters. We can find age enters the model. And you can see that various other, especially all the other models, you can see it is less. But when you add X2, there is a still reduction. You can see that X2 actually brings down the KS value in step 2. So it brings down to 0.4125. I have indicated that in a gray color. Next slide. The third one is GGT. The GGT enters in the third step, where we are able to see an increment in the model. So 0.6 is what you get in the third stage. In the fourth stage, next slide, we can see that either X2 or X1 or X6, I'm sorry, X2 or X4 or X6 or X7, all of them can enter. In fact, all of them lead to the same incremental KS value. So all of them are possible entrance into the discriminant model. Next step. When you go to stage 5, you can see that there is absolutely no increment in the KS value, and therefore we are going to stop with the step number 4. After step number 4, no additional variables enter. So next slide. And these are the 4 models that we get. One includes age, TGL, GGT, and weight. Another one includes age, GGT, height. Actually, age, GGT, and weight, these are all common for all the models because they entered in the first 3 stages. In the 4th stage, we have an option. Either we can go for TGL or we can go for height. We can take any one of them. It throws up so many models with the same equal discriminatory capacity. And the next sequel, I'll just complete in 2 minutes. Unequal prior probabilities are considered, reflecting a closer picture of the actual composition of FLD people and non-FLD people in the general population. Next slide. Here also you can see X5 enters first. Remember, the computations will be totally different because P1 and P2 are taken differently, not equally. Next step. Again, age enters. Then 3rd step. GGT enters. So pretty much the same. Then the next slide. You can see only 2 variables are entering, whereas there we saw 4 variables coming into the model. Here only 2 variables are equally competing, triglyceride and waist circumference. They come into the model with equal strength and the Ks is 0.6125. Next slide. In the next slide, you can see there is no further improvement and therefore no additional variables enter, and the variable building, the model building will be there with only 4 variables in the model. Age, weight, GGT, and triglyceride or waist circumference. One of them could be an entrant into the model. Next slide. And these are the 2 model equations we get. Again, you can see that models with the satisfactory, a good discriminatory capacity is thrown up by this method. We note that even though the variables under the 2 prior probability schemes may be exactly the same, almost same only we are getting, but the model coefficients may be quite different in the 2 approaches. We refer to examples, models D and model F, you can just check that. It is quite possible that when prior probabilities are chosen still closer to reflect reality, the resulting model might perform still better. Next slide, please. We compare with logistic regression. It throws up 4 variables, weight, age, GGT, and waist circumference. Again, pretty much the same, but the Ks for this model is 0.4625 only, which is lower than the Ks 0.6125 achieved by all the 6 discriminant models derived in the new approach. Next slide. It is interesting to note that the optimal discriminant models D and F are based exactly on the same variables as the above binary logistic regression model, but has a higher discriminatory ability as measured by our Ks statistic. The other optimal discriminant models A, B, C, and D are based on different subsets of variables, each of which overlaps with the variables in the logistic regression model. Not exactly same, but it overlaps. Still, performance-wise, all those discriminant models are equally good and give better performance than logistic regression model. Next slide, please. References. This candidate, Mr. S. Padmanabhan, who is working in ICMR. He is my PhD candidate, and along with him, this work was carried out. I thank him for the data that he brought up for the study. Thank you all very much. Thank you, the organizers, for the opportunity given to me. Thank you, Dr. Thangaraj, sir.
Thank you, Williams.
Thank you,
it's a very nice talk. Sorry for the interruption by
no problem, sir. No problem.
PPT. No. The problem is you have used that screen moving after screen share, but you should have done immediately after opening the PPT. You start seeing left hand corner and then share the screen. But ulta operation will not be accepted in Zoom. That is the whole problem.
Okay. Sorry.
Otherwise, you go to YouTube and then see that how to use PPT in Zoom. That will explain very nicely. Okay. Except that,
Thank you, sir. Thank you, sir.
your talk is very nice. Okay, I
Thank you
also
very much,
thank the organizer for coming for rescue operation. Okay.
Definitely.
Thank you, Suresh. Thank you, Ramadurai.
Yes, sir.
Right. Now, any questions, please?
Professor Tangaraj, can I have a question?
Yeah, please.
Yeah, Professor Martin,
Yes, sir. Yes, sir.
that was a good talk. I have a very small question. See, the Kolmogorov-Smirnov statistics has a problem because it's basically capture the deviation at the supremum, the supremum of fnx minus fx. So as a alternative, Anderson-Darling integrate out the whole of this, because integral fnx minus fx whole square dfx, that's actually the Anderson-Darling. So if you use Anderson-Darling, do you think that the discrimination would be much better as compared to this? Have you tried this or?
No, I have not tried, sir, but I think it is a very important question that you raised. Definitely, I think we have to take it up. I have not considered this so far. Definitely, I think it should be possible to go in that direction also to check out how the discriminatory capacity comes out. We have not done that so far, sir. Thank you very much for the question. Definitely, it gives us definitely a good input for us to proceed further. Thank you very much.
Is there any other questions? I assume that there is no further questions. If at all any questions, you just to post it to the organizers. In turn, they will forward the questions to Williams for clarification. Thank you very much, Williams.
Thank you, sir. Thank you, Dr. Tangaraj, sir. Thank you, Dr. Amadurai and Dr. Suresh for coming to the rescue, as Dr. Tangaraj sir said, because we have been working on Google Meet for our online classes. Zoom is something very different for me. Anyway, thank you very much, sir. Thank you. I hope enjoyed the session.
Yes, sir. It is our duty, sir, and thank you so much, sir, for having accepted our invitation, sir. Thank you very much, sir.
Thank you, and thank you. I'm nice to see Dr. Suresh Chandra. Dr. Suresh Chandra was my Viva examiner for my PhD. Sir, namaskaram, sir. Dr. Suresh Chandra.
Okay. Shall we go to the next speaker?
Yes, sir. Yes, sir.
Thank you, sir.
Yeah, now I have a great time. See, mathematics people play with the numbers, but whereas statistics people are playing with the figures. Now we have seen that how Williams has played with the figures. Right now, we'll move on to next speaker under the same SPR. SPR is the short name we used to call him. SP Rajagopalan Endowment Lecture. Professor Ramanathan. I think he has, yeah. Yes, he's a Professor Ramanathan is a professor and head of Department of Statistics, Savitribai Pune University, Pune. He had his all basic education, so BSc, MSc in Statistics from Kerala, MPhil and PhD from Kerala University. Then he has got many honors and awards. Erasmus Mundus Fellowship from European Union to visit Leuven, Belgium, and then qualified national, NET, and then junior fellowship from UGC. And then his research area is inference in stochastic processes, finance and time series analysis, non-parametric inference, econometrics, and big data analytics. Good. And he has published 2 books and articles, more than 50. Now, we are all very eager to listen to the scholars' delivery of his lecture. Professor Ramanathan. Ramanathan, please.
Thank you, Professor Tangaraj. I'm audible, right?
Yeah, you are audible. I don't know for the others.
Sir, yes, sir, audible, sir.
Yes.
Okay, fine.
So thank you, the organizers, for inviting me. Thank you, Professor Suresh Chandra. I'm seeing you after a long time.
UG second year.
Yeah.
UG
So,
second year.
UG second year.
So, can I start the talk?
Sir, UG second year.
My screen visible?
All others mute the mic.
Yes, sir.
Except the speaker. Yes, please. No. Ramanathan sir, please. Ramanathan sir, please. Yeah.
Yeah. Actually, yeah. Okay. So, so the title of my talk is Probabilistic Frontier Regression Models for a Count Type Output Data. This is something, this whole thing I have learned from Professor Suresh Chandra when we were together in Botswana, and then I could publish a couple of papers. So this is some new work that we have done in the recent past. So my collaborator for this work is Mrs. Meena Badde. So I'll take you through the problem, the stochastic frontier model and the efficiency, the probabilistic frontier for count output data, model and technical efficiency, some simulation study, and an application. So consider a situation that we have this type of a data where you have the count. So for example, this is the number of crimes. This is published by NCRB, National Crime Research Bureau. It's, of course, their data is not like this. This has been changed because of this. The counts are per 200 kilometers area, depending on the state's area, and then we have actually arrived at these figures. So there are about 25 states that you can see in this. And this is the panel data. It's about 8 years from 2012 to 2019. So the basic in probabilistic frontier regression, basically the stochastic frontier regression, the idea is these are considered as units, and then you try to have how efficiently they do the production. I mean, that's what in econometrics they call it as. But here it is being applied in various different field or different topics. So, and then to compare kind of the decision, they call it as decision-making units. So here your decision-making units are the states, and then you would like to know how efficiently they are addressing or controlling the crime. That's what the topic. Now, let me have some history of this whole thing. So basically, this is like a conventional econometric trick where a production function is used. And then in the production function, usually it's like a regression function. And in the regression, we look for the average or the mean, like expected value of y given x. But here, on the contrary, the two things are different. Here, I will look for a frontier in the sense that I will look at the maximum or I look at the minimum, depending on whether you are addressing the profit or you are addressing the cost. And then try to see that in regression, we are not worried about what is happening with the individuals. Whereas here, the interest is how individual units or decision-making units are efficient in addressing this particular problem or the issue. So it's like you are not just interested in an average, but you are interested in individuals. See, that changes the estimation problem into a difficult one. So this is what roughly the idea of stochastic frontier regression. Now, all these things, basic idea is not get an exact number which represents the efficiency, but basically it's for a kind of a an understanding that where you stand in a peer group, so that if you are much below, you need to have some corrective measures. If you are much above, definitely you need to follow that as a benchmark, etc. Okay. So this is a powerful tool, and it has been applied in various fields. In a minute, in the next slide that you can see, this whole thing started with a paper in 1957 in JRSS by Farrell. And this is basically, it's like, how efficiently you can increase the production by, so it's like among the peer units, which are using same kind of inputs, and then try to maximize the output. Or so naturally, it's look like an optimization problem where you have input and then output, you maximize the output for the given input. So there are two approaches for this, which is one is called data envelopment analysis, which is like, as I was telling, is an optimization problem using linear programming techniques. But on the other side, statisticians looked at in a different way. They thought that this frontier that you are considering cannot be a fixed one. So you should look at a stochastic frontier and then consider what is called as stochastic frontier analysis. So if you look at that, this whole thing started in 1977 by these authors, Egner, Lowell, and Schmidt, generally known as ALS. And then there are a lot of people who started working on this. So the basic idea is that you have y equal to fxi beta e to the power of vi multiplied by a factor here. So this essentially this vi represents a kind of measurement error, which is generally we assume that is normal. And the TEI, that's what the technical efficiency, how efficient that you are. So it's like, you know, if you look at the scatter diagram in a typical two variable regression context, simple regression context, you try to draw a line which actually in the middle, generally we say that it is expectation. So it's generally in the middle, of course, depending on the cloud of the data. But here what we are trying to do is that we are trying to draw a line which is on the top, and then say that how each of the units are away. So if you are much below that, you basically have less efficient. And if you are close to that, because the one which is the line that we have drawn is the most efficient, something similar. I mean, that's what. So it's instead of looking at the average, we look at the frontier. So that's what the whole idea is. That so naturally the frontier is like, if this is not there, if the efficiency, I mean, like, basically I will look at a kind of ratio between this yi and fxi beta, apart from this particular error. This error, of course, we assume that it's normal and all. And generally, in econometrics, they go for a Cobb-Dowlus kind of setup. So you take logarithm of this, that leads to something like a linear, a simple case, it's a linear kind of a model. So this is what the quantity which is actually troubling over here, in the sense that which pull down from what you are supposed to be. So you are supposed to be here, which is the expectation, but this actually is a non-negative random variable which pull down from that. And this is the whole idea of these people. Sorry, I'm sorry. The whole idea of this these pioneers who actually started this research, what is called as stochastic production frontier or stochastic frontier model. Now, the thing is, what is being done, I mean, from statistics point of view. So generally the least square estimation can be done, but least square estimation has a problem, because if you take this as an error, this has a non-zero mean, so that it has to be adjusted. So that makes some kind of identifiability problem. So you may have to do some correction. So that is what the corrected least square. But then it has its own difficulties, like how to get the individual inefficiency. So that's something which is stopping, because least square basically gives me estimates for this alpha and beta. So individual getting, I mean, the error or the what you call the inefficiency will be a bit difficult. Another approach is the maximum likelihood, which is the commonly used approach, that you consider a particular type of this is of course a measurement error, so you assume normality. This is basically an error which is actually on a positive side, because that is what the inefficiency factor. So you can have a convolution and then write down the likelihood, maximize the parameters, etc. This is what is being done. But then that plays an important role here, what to choose as this parameter, I mean, this the distribution for these innovations or these errors. So of course, we assume that they are independent, but that choice is basically crucial. So then how do you actually, once you get this, as I told you, it is not the problem is not just the estimation of the parameters. The problem is to get a measure for inefficiency. So people suggested different measures, like when they started this whole development, I mean, you suggested 1 minus E of U, which is like a common measure, average technical efficiency. This is also an average technical efficiency. Now, individual, if you want to get it, you suggested, I mean, like these were suggested by e to the power of minus UI hat. That's what the technical efficiency. This is, of course, this E is coming because of this Cobb-Dowlus nature for the function. So ultimately, Battis and Coyley suggested something like this. Okay, so there are various versions of this. Various developments happened. And this has been taken from cross-sectional data to panel data, etc. by Kumpagar and all. And those who are interested in this area, there is a book by Kumpagar and Lowell, and then there is a recent review by Kumpagar in 2018. So you should look at this. Now, you may wonder, oh, this is a very remote area of this thing. I mean, that's not the case. If you look at the application, it's tremendous application. In fact, if you look at any applied econometrics or even applied statistics journals, you can, in fact, there is a devoted journal for this production, related to this particular stochastic frontier analysis. So you can see, I have written just some of the application in various areas: banking, telecommunication, agriculture, fish production, healthcare, energy, chemical data, higher education. And these are just recent one. And you can see that right from the beginning 70s, this has been applied in various contexts and various applications that you can see. So basically, this is applied when you want to have peer group and then make a comparison about their efficiency, how efficient they are in doing that particular production. So this is applicable to even higher education institutes, like how efficient they are. So naturally, there are inputs and there are outputs, and then you have to decide the efficiency based on the model. Now, as I was telling, there are a lot of development in regarding the choice of UI. So these are some of the development over the period of time. We also contributed a little bit here on using an inverse Gaussian and log normal frontier, and then try to develop the whole thing. It's not very easy to, that's why every time you change a distribution, like you need to write a paper, because the development of that actually quite involved. So it took a long time from 70s to 80, from coming from half normal to gamma, and then gamma to other Weibull 2006, and then we looked into log normal, etc. Well, that's the old story. Now I'm coming to the current problem. Now the problem is that instead of the continuous data, I want to extend this whole idea to generalized linear models, where I will be looking at binary data or multinomial data or count data. So for example, I may have a binary where I have good and bad. So what we know is the output is like a good and bad. And then you need to come up with the efficiency. Say, for example, regarding the banks. Now, there is a benchmark for NPA kept by Reserve Bank. So now, if you are above the level, then you are basically above that particular level, then you are actually a bad. If you are below, then your bank is supposed to be good. Now, if you have only this data, can you compare the efficiency of the banks? This is one question. Similarly, the same thing can be applied to a multinomial setup where I have, instead of just 2, you have k different outputs, which is in a ordered manner. It could be ordinal, or it could be simply, like 1, 2, 3k. And then can we have an efficiency theory developed for that? A third question is, now extend this to count situations. So count means I have 0, 1, 2, 3, etc. Like what I have shown in the beginning. I have a count data, and then I want to develop a theory for this. Now the challenge here in all these things, unlike in the case of continuous case where you look at the expectation, the technical efficiency that what we consider is not in terms of the expectation, but we may have to look at the probabilities, because for example, in a binary case, expectation is nothing but the probability. So you look at the case, for example, the probability of getting 1 or good is now coming down, which indicates that there is a loss in the efficiency. So something similar you can apply to multinomial, something similar that you can try to apply to the count. But the problem with multinomial or count, in the case of binary, it is somewhat easy. But in the case of multinomial and count, what is required is that you need to consider a particular selection of output in which you are interested. Otherwise, what happens that if these probabilities come down, naturally the other probabilities will increase. So something like for Poisson, lambda 1 less than lambda 1 greater than lambda 2. So you see that this is unfortunately the notation is bit happen to be same, but I'm sorry for that. So here, for example, this is one curve which is coming like this, and the other curve is exactly on the top of what we have drawn. So what you can see that here, when I reduce from here to here, when it comes to here, it actually go above that. So that's what the problem is. So essentially it is above here and below here. It is below here and above here. So it's very clear, because the probability when you try to reduce certain things, then naturally the other side is going to increase. So in such a situation, this average considering is not a good one. So that's where we change the whole idea from average to probabilities. So probabilities in the sense that you look at the probability of certain class and then try to see that how I mean, what is the change in these probabilities and relate that to the efficiency idea, the efficiency. So that's how, so that requires a new definition for efficiency, as well as how you look at these probabilities. So this is the whole problem. This forced us to have what is called as interest class. And interest class is something, the class for which I will be looking at this probability. So I may not be interested in the other class at all when I define my interest class. So interest class is like, you can also relate to economic good and economic bad, because interest class is like, for example, in a pollution, I will be looking at the pollution where pollution is less, that is better. Whereas if you look at a research output, I will be looking at the more number of patents or more number of publications. So the class will be lying, depending on the problem, where that particular class lies. Okay. And then you look at the change in those probabilities of those class. And so that's basically, so we renamed this stochastic frontier as probabilistic frontier, because we will be looking at the probabilities. I'm audible, right?
Yeah, it is fine.
Yeah.
Yes, sir, you're audible, sir.
Yeah. So these are, in the binary case, we have published a paper recently, which appeared in Applied Statistics. So I'm not getting into that. In the multinomial case also, we have published a paper in the Journal of Productivity Analysis, which appeared last year. So that's what these two work. So now we are looking at count case in this today's presentation. So when you look at the count case, are there some earlier work in this direction? If yes, how this can be, I mean, how this is not applicable in our case. So there are basically there are two papers in this context. One is by Hoffler in 2013, where he considered a PHN model, Poisson half normal model. What he considered is that the Poisson parameter lambda is modeled like this. Log lambda is hx beta plus or minus u, where u is the inefficiency component. Of course, he doesn't address the panel data. The another paper which appeared very recently, in fact, we were not even aware of this, which appeared in a textbook or edited volume. So when we submitted the paper only, we came to know that there is a paper like this. So there they actually considered something like this, and then tried to come up with the, the inefficiencies. But what happened, the main, if you look at the thread of these two, they are considering, even though the data output is like a count one, they are now connecting that to a continuous kind of a model, or then going back to the efficiency and other things in the typical continuous case by making some adjustment over the overall lambda. So what you see is that here the changes are for overall lambda, but they are not worried about what is happening to individual classes or groups. But what we thought that is more important in the case of count or binary or multinomial data. So that's why where we changed our approach. So you see that there is an interest to study. For example, these problems are very important. Like, for example, in economics, the change in probabilities of a particular outcome or few outcomes in the presence of stochastic inefficiency component. Say, for example, variations in international labor mobility. Or another problem that you may address is that Poisson may not be enough, because there is a over dispersion, under dispersion for this kind of data. So that is another issue. So in order to address in three directions, one is like, instead of average, we want individual. Instead of like Poisson, we would like to have over dispersion and under dispersion considered together. Instead of cross-sectional, we want to look at panel data. So this 3-dimension extension we thought, and that's where we actually introduced a model based on CMP or Convoy Maxwell Poisson model, where the advantage of this is like, it's like more parsimonious in the sense that over dispersion, under dispersion, and equidispersion can be considered in one go with a parameter nu added to that. Those who are working in CMP distribution, they will be knowing this. Another thing is that it is in the exponential family. It's also in the two parameter power series family, and there is a conjugate prior. So life is, much more easy in this case. So we thought that we should treat whatever output in the format itself, that if it is discrete or if it is multinomial, we would like to continue it like discrete or multinomial, rather than comparing that with a cut version of a continuous thing and then develop the efficiency. That's what earlier papers did. So we did not do that. So we considered in this particular manner. And then one difficulty that we have is this particular term, which is basically, is an infinite series. So when you actually apply, you need to have some kind of a, adjustment over here. So let's see the interest class. And then what we are considering is like, of course, we also get these things. But as I told you, that's a part of the development. But then when you get the technical efficiency, we have defined it in a different way so that individual units efficiency can be computed. Okay. So the mod without resorting to the continuous case, we are still in the discrete output. So this is the probability, the conditional probability of y given x, and all this. This UI is basically this one, the inefficiency which is unobservable. And then here, because of a panel, I have to do some adjustment. I have to have a adopt a parameterization for UIT, because I cannot vary it completely. So we considered something like this. This is a question that one can challenge in the sense that why we should have this. Well, apparent answer is like, if I consider it fully I and t varies, then I may not be able to estimate individual one. So that's why some kind of a parameterization is done so that we will be able to get them. Okay. Well, these explanations are there already in the stochastic frontier in the continuous case. So we adopted in a similar manner. So we have the likelihood, which is here. And because now you see this so complex, the likelihood is. So maximum likelihood we tried, but we were not getting good estimates. Perhaps maybe with some more advanced computing methods, we will be able to do, but we are yet to try that. But so we directly went for a Bayesian model here, because Bayesian, one advantage of Bayesian is that you can treat UIs as parameters and then you can do the inference for that. So we went for the Bayesian, and we have these priors. Of course, these are not completely, we just decided arbitrarily. We have actually looked into the literature, and then fortunately I told you there are some conjugate prior for this distribution, so we can actually make use of them. And because of our setup, regression parameters are generally assumed to be a normal prior, and this new, that is a dispersion parameter, which is assumed to be a log normal, and then eta, that's a truncated normal, and then this is a 2-parameter gamma, that theta. So there are 4 parameters here that you might have seen. That theta is, so there are 4 parameters. Yeah, so 1, 2, 3, 4. 1, 2, 3, 4. And then U is like inefficiency, which is unobservable. So I get the posterior. We treat them as parameters U1, U2, Un. And then U1, U2, UT. N is the notation, T is the notation. So you can develop this, and then this you can apply an MCMC, fortunately. Well, I'm not jumping into the MCMC and then say that MCMC will solve everything. No, we had enough, the diagnostic procedures applied here so that we make sure that the Markov chain converges, there is still the series is stationary. All these things have been done, because otherwise I don't really approve this MCMC blindly unless you do all diagnostic procedures. So estimation using MH and then the Gibbs algorithm. And here is where we differ very crucially, in the sense that technical efficiency, I could define it in this particular manner, which is basically, it's not that generally it is defined as a ratio of expectation. It's like replacement policy reward is defined. So something similar, expectation with the inefficiency component and expectation without inefficiency component, the ratio is taken. This is what the general gist of the paper by the Battis and Coyley. So we actually went for the corresponding probabilities and then defined it in this particular manner. And in the economic bad case, you see this economic bad and economic good decide where you actually consider the YIs. So that's why, you know, you have this in the beginning or towards the end. I told you that depends on the kind of problem that you are dealing. You have to define the class of interest, because
Sir
in the production,
please, you take a few more minutes to.
Sure. I'm almost done. So this is the simulation. So we have seen that you are getting the posterior means very close to the true value. Of course, there are some diagnostic things here. In all the three cases, I have three cases. One which is over dispersed, under dispersed, EQ dispersed. Okay, that the new parameter basically tells you over dispersed, under dispersed, EQ dispersed. And you see, this is basically the posterior predictive distribution of the UIs, and then you see that this is very close to the true in all the three cases. So these are three graphs that I have, all the nu less than 1, nu greater than 1, nu equal to 1. Now I am trying to apply this. Actually, we started with the application. So I'm now coming back to that application. We want to have some efficiency of the states in handling the crime. Now, you know, when you take a real data from government, there are a lot of limitations. So we also have those limitations with us. So it's like limitation is Jammu and Kashmir has become already a union territory. Then you have very less data, in fact, not less. Most of them are zeros. When it comes to Arunachal Pradesh, Nagaland, they are omitted. And in between, Andhra Pradesh and Telangana got merged. So because we have a panel data, 2014, I think they got merged. So we have combined them and then put it as an Andhra Pradesh. So in all, there are about 25 states, and 3 crimes we have considered, rapes, and then the crime against children and the assaults on women during this panel period of 8. So basically, you know, I mean, I think I already explained the output. The input considered are the vehicles, stations, police personnel, computers, etc. SDP also, stage domestic product. These are available from the SDPs from the Reserve Bank of India website, and these inputs are available from Bureau of, you know, Police Research. There is a website which is actually maintained by police, Bureau of Police Research and Development. So you can get these details state-wise. And then we run different Poisson regression to identify which are of them significant. In fact, we wanted to have 2 more input, which is like, because crime is basically dropout. Sometimes we say it as a consequence of dropout, school dropout. And then another thing is like, high school dropout, and then unemployment. Unemployment also can lead to crime. But however, there was some problem with the data. We were not having all the observation available, or some of them are really not really very good, especially when it comes to dropout. So finally, we could not consider these 2 inputs. So we have actually considered these inputs. And then this is the kind of efficiency that we compute for the states. So you can see that from the given data, let me be very cautious. I'm taking from the given data, what we could see is that West Bengal is, which in all the 3 crimes that we have considered, West Bengal is dealing the crime much better compared to the other states. Of course, there are Tamil Nadu, I think, here, not bad. Then there are some of the other states. But you can see that there is something that you immediately see, 2 columns here. 2 rows here, Goa and Kerala are become 0. Why it is so? So I'm going to explain that in a minute. So some of the problem that we faced, the average, so this average is about 68, 59 here in the case of rapes, and then assaults and women. This is the average, and individuals are this. So we can have a comparison, and the one which is very less, we need to look into what is the problem, how that can be improved. But this methodology is very limited in the sense that we are still working on that, because this actually throws some light to us why this 0 is happening. The 0 is happening because if you look at, we have considered overall median as the point up to which we should travel and consider the interest class. Now, what happened that In these states, all the observations are above that median. So we could not get an interest class identified over here. Now the question is that then immediately somebody, oh, you can change the interest class for every state. Well, that actually changes to a heterogeneous situation. So now we are working on heterogeneous frontier model, how that can be used in this particular case. And that is what really we needed in these kind of situations. So we could not get a measure here. That doesn't mean that they are inefficient. One reason could be all the crimes reported could be, I mean, like very high in these states. Either it could be a reality or it could be reporting is good, registration is good. And therefore, it is much above the overall median. This is what's really surprising to us, these two states. Whereas this is not happening with many other states in these kind of crimes. Of course, we also considered some other crime. There it happens. We actually consider cyber crime also. There also only 2-3 states, 2-3 states have similar problem. So we won't get a comparison across. So that's why we actually kept it aside. Well, I think that's what it is. So future direction is how to extend this to heterogeneous situation. Yeah, that's all from my side. Thank you very much. Any questions? I'm happy to answer.
Thank you very much, Professor Ramanathan. Very nice. You are biased, I think. You have taken only crime on assault on women. What about assault on men?
Yes, sir. Yeah, actually, you know, we were trying. Yes, sir. We can take it. What we thought initially, let me tell you very frankly, we initially thought that we only consider a crime against women. So rape and assault on women we started working on, and then we found these zeros. Then we realized, oh, we need to consider something else. But assault on women, men as such, is not very important in the context of NCRB data.
Yesterday I saw a newspaper item. One woman from Kerala carrying the head of her husband by just getting the head to the police station. Okay, that is why I'm telling assault on men. Right?
Yeah, maybe
that also needs attention.
Actually, it depends on NCRB data because NCRB generally say assaults and assaults on women. So maybe we should actually, change that assault on men.
Yes. Okay. Any other questions or discussion, please? Vishwanathan, you want to ask something?
Yes, sir, please.
Yeah, please.
Sir, it's a wonderful lecture covering both the non-parametric and parametric aspects simultaneously and enlightening about the technical efficiency. So I have two doubts. One is when you assume the component UIT as a two different function, one involving separately I and one involving separately T. My doubt is whether will it not break the structure of the panel?
Yeah. So actually what happens that if I include, see, this is what I assumed is something like this. I'll show you that in a minute. Yeah. So if you look at the last line, generally you can actually go with T also changing and then consider it like, you know, a kind of including I and T. But what has happened that if you consider that, we may not be able to get individual because there is some kind of an averaging has to be done across the panel. Otherwise, you can't really estimate those parameters because you have to get individual efficiency.
But the thing is that once you estimate UIT, can you sum it over T and get I?
But that is again you are doing it, like averaging across the time now, assuming that they are. So somewhere we have to do that. So we thought that we did in this particular way where we parameterized it in this particular way. But as you said, there are different options here for this gamma T. We just followed the earlier continuous time, econometricians, what they tried to use various functions for gamma T. And one of them we found suitable to our situation is something like this. Well, you can go for e to the power of a plus bt. There are various types that actually depending on the problem, because we also see that as time changes, whether your individual units learn something so that they become more efficient. So accordingly, you need to change it. So what I mean, like if policing has, like, for example, if number of polices increases, there is a feeling that the crime may reduce it. So you need to actually assume that I should have some function which actually take care of this. So for the time being, we use this and then see that how it is efficient. Well, there is an option that one can actually go for different gamma T and then looked at the problem.
Yeah, okay, sir. And one more thing is, we are taking different crime rates or different variables in general, and whether any multicollinearity among themselves, will it affect the estimation?
Yeah, that's a good question. Actually, there is some kind of a multicollinearity effect. That's a good question. Actually, in this case, what we have done is, we have actually, see, when you actually use that government available data, you don't have a control on that because this is not a design thing. So generally there can be a multicollinearity effect over here. But fortunately in our case, these things are the variable that I have chosen, vehicle, stations, police personnel, computers. It didn't show much of multicollinearity, but you are right. We need to actually, because once it is chosen, I mean, basically, it's like how you choose the input. This is the question that.
Yeah.
So once it is chosen, actually the multicollinearity doesn't play any role, because the reason is that once it is chosen, of course, while choosing it plays a role, because I am not using any least square estimator or OLS or things like that. What we do is that, I mean, we have a model which is a stochastic frontier kind of probabilistic frontier model, and in that we are estimating the parameters using the Bayesian setup. So I don't have a problem of inverting, the incidence matrix or something like that. So as such, it doesn't affect my mathematics of that. But you are right, choosing the input is very important, because how do you choose that? Now, in a given data set, we have to restrict ourselves. So definitely there can be more multicollinear situation can arise if we consider, like, for example, unemployment rate and SDP may be related. So if I consider, so, I mean, I have to be careful about that. So we need to look into that, how multicollinearity, if it is there, how to choose it. But what happens that stochastic frontier or probabilistic frontier starts with having a set of input and having a set of output. When you extend this problem to an application, that's where we have to be worried about how you decide your inputs. So input decision is actually an important entity, because if you change your input, your output, I mean, is going to change. So definitely the inefficiency and efficiency depends on how good you choose the input. So I agree with your question. We need to be careful in using that. However, I did not face much of the problem. Perhaps if I elaborate my inputs, I will face this problem, and then we need to find this usual procedure of multicollinearity has to be adopted. We run Poisson regression to come up with this. So all significant variables are selected here. Several Poisson regression we run for individual year as well as for some of the individual units, and then try to see that which of them are more significant. So whichever turned out to be more significant, we selected for this analysis.
Thank you. Thank you very much, Professor, for your exhaustive explanation.
Thank you.
Sir, I have one question.
Yeah. Yes.
Yes, I have one question to sir.
Sure.
Sir, myself, Sandesh Kurade. I want to just to ask you one question. Here, you have an aim like to obtain this TE for the various crimes. So basically, the crimes,
Not crimes,
it is
for
nothing
various
but,
states.
yes,
In
various
handling
states.
that particular crime.
Yes. But so this is actually count data.
Yeah. Yes.
It is actually count data. But suppose we have the counts according to the say time. So if the count depends on the time. So whether it is process time model is suitable or
I can't hear you, Sandesh.
Sandesh, your audio is not good. Not audible.
Okay, now it is good. Now.
No.
Now it is audible, sir.
No, it is it is a disturbed noise. Almost broken.
Sandesh, I mean, if I understood correctly, of course, I couldn't hear what you are talking. So basically, I mean, I think you are asking like if it is a count data and then it is depending on time. Well, what we have done is we have actually modeled that time dependence by a particular functional form gamma t. Now, there is also always an issue. How do you choose the best gamma t for a practical situation? If you are asking that question, well, right now I have adopted the usual one which is there in the literature. One can play around. In fact, that's the same question Dr. Vishwanathan also asked. So, well, we need to actually look into that.
Okay. Professor Sureshchandra is on the line now.
Professor Sureshchandra, nice meeting you.
You a long time, Ramana.
Yeah. How are you?
I have a basic question.
Sure.
In the stochastic frontier model, we use the linear model.
Right.
Classical. What will happen if we use generalized additive models?
What will happen if
we use generalized additive model, so that you will not have beta 1, beta 2, beta k, but you will
actually I have used generalized linear model only. But yeah, that I haven't tried. Maybe that we need to. The next step is extending this to GAM.
Yeah. What happens there is perhaps we may miss some of the niceties of economic assumptions like productivity conditions.
Yeah.
We may lose it because unless they're all monotonic, suppose
right.
Smooth functions of
in fact, that is what we face the problem. So I did not consider like econometricians, because when some probabilities reduce, other probabilities increase. So we have to have a class and then define the efficiency for that class. In fact, I was trying to talk to several econometricians that do you have a similar kind of a situation? Most of them say that we don't really have this problem. We consider all normal. So there is no issue of this discrete or count situation. So you are right that monotonicity is lost in that case.
See, what happens is when the smooth functions are not monotonic, your productivity theory gets affected.
Correct.
So just because we have a good model, good methodology, we should not apply it here. We must also have in background the economic conditions, right? So
right.
Just I was thinking whether that could be done with some caution.
Yeah, perhaps I should try that as a next step. So we look from the application point of view, what GAM, generalized additive models, basically try to connect that to the econometrics. Because here also I had a tough time in actually connecting, because how do you actually, because most of the people say that, okay, there is efficiency and it is continuous. I mean, you consider the continuous case. So I try to see that, okay, how probabilities are changing. So look at the probabilities are changing. Because I have certain fixed probability for good things to produce or good things to happen, and this probability come down, which means that there is an inefficiency factor coming into the picture. So that's the crucial thing. And this I try to apply to a multinomial setup as well as count setup with appropriate definitions.
One more question, if you don't mind. See, if you look at probabilities instead of estimating UI caps or anything, perhaps some of these conditions, economic conditions, may not be necessary in a general efficiency model, but perhaps it may not have any applications in economics, but theoretically you'll be solving a problem. No, I don't know. I mean, I was just thinking about it because we tried something, but I didn't succeed.
Yeah, I think we need to look into that. I haven't really, because first I thought that I should come up with an econometric kind of an application and then develop it from there.
Yeah.
Yeah. Need to look into. Thank you for that suggestion. Maybe
we'll
be looking into that.
Thank you. Thank you very much.
Yeah.
Oh, very nice. Sir, your sessions are going to polish his arguments, polish his presentation. It's an excellent discussion that we had today. And therefore, I hope I did my job of Nilaya Vidwan. So, I think, sir?
You know that Ramlada is very much interested in music.
Hi. Oh, is it? And you know what I mean by that. Okay, now we thank both speakers for their wonderful and exciting, interesting talk for the benefit of statisticians, younger statistician and working statistician, and also elder statisticians like us to have more enlightenment on the statistical methods, whether it has to be analyzed in a probabilistic way or in a statistical way with using a lot of statistical figures and other things. Now, I thank you very much to both speakers in a very large measure. Now, I call it a day. Thank you.
Thank you, sir.
Thank you, sir. Dr. Thangaraj, sir. Thank you. Thank you very much.
Thank you, sir. Sir, it is our sincere duty to thank respected Professor Dr. V. Thangaraj, sir, former Director and Head, Ramanujam Institute for Advanced Study in Mathematics, University of Madras, for having accepted our kind invitation immediately to chair this session of Professor S.P. Rajagopalan sir's endowment lecture. Even at your small health alienation. Thank you very much, sir. Sir, also, as you mentioned, we never feel that you are from the Ramanujam Institute, but also we feel that you are also the part of this statistics department always said. I personally remember that, if I'm correct, the present computer lab of this department, your vision is also there, while Professor, the former HOD of Statistics Department, Professor G. Gopal sir's effort while constructing this lab under this DST FIS program during his headship. Also, without your August presence, no academic event will be possible, and your today's chairmanship is also one of the evidence, sir. So thank you so much, sir, for your kind accepting your invitation to chair this session. Thank you so much, sir, once again, sir.
Thank you, sir.
Thank you very much.
Yes, sir. Thank you so much.
Okay. Let us meet, let's contribute the session and then valedictory function. Okay?
Yes, sir.
This concludes the contributory session for the day. We will have 2 contributory sessions, and separate links have been sent to the participants. The session will start at 1:40. Thank you. Thank you, sir.
To all. So on behalf of the organizing committee, I welcome Professor N. Viswanathan, sir, Associate Professor and Head, Department of Statistics, Presidency College, invite to chair the contributory session 1. Now I introduce Professor Viswanathan, sir, briefly. Dr. N. Viswanathan, sir, did his UG and PG at Loyola College and PhD in Statistics at University of Madras. Sir is qualified as a CSR UGC net lecturer, and sir has 26 years of UG teaching experience in UG and 25 years of teaching experience in PG. Sir has published 12 national and 6 international articles in reputed journals, and sir has served as a research officer in schizophrenia prevalence study conducted by Indian Council of Medical Research, survival analysis, informative sensory. So with this brief introduction, I request Professor N. Viswanathan, sir, to chair the sessions. Thank you, sir. Sir, your mic is mute, sir. Please unmute your mic, sir.
Thank you, Professor Suresh, for your kind words. And since we are running out of time, I think we can right away get into the business. And
Yes,
see, we have 20 participants to present their papers. So I think each participant, at the most, they can take 7 minutes. Okay. And we can have 1 minute for question and answer session. Okay. So that's the way we have planned. And I will first ask, I will go by the list provided by the organizers. And the first candidate is Dr. Giju Glorios. Okay. And the topic is a new distribution derived from the arc cosine function.
Good afternoon, sir. Good afternoon, all.
Yeah, please proceed, madam.
Okay. The title of my presentation is a new distribution derived from the arc cosine function. So please go to next slide. So we know that there are so many distributions in statistical literature, but distribution with bounded support is useful when you are handling data set which can be modeled by bounded distribution. So in this work, we introduce a new distribution on the interval 0, 1. Sir, please go to next slide. We know that there are so many bounded distribution. For example, uniform distribution, truncated normal distribution, beta distribution, Kumarasamy distribution, beta power distribution, log linear distribution. These all are examples of bounded distributions. In this work, we introduced a new distribution bounded on the interval 0, 1. So next slide. So here we know that arc cosine function is a inverse of cosine function. Here we denote g of x as arc cos function. That is, we can see that this g of x equal to arc cos, following all the properties of probability density function, that is g of x greater than or equal to 0, and its total integral equal to 1. And also we can see that this distribution have decreasing and concave shapes of its PDF. Sir, please go to next slide. So in this paper, we will introduce a new distribution using this transformation, that is f of x equal to alpha x raised to alpha minus 1 into g of x raised to alpha, where this g of x is equal to arc cos x. That is, our new distribution is bounded on 0, 1. This is the probability density function. This equation number 1 represents the probability density function of new arc cos distribution. We can also derive its distribution function from corresponding probability density function, and also derived its hazard rate function. We derived some properties of this probability density function. From the analysis, we can see that this probability density function is so sir, please go to next slide. Is decreasing and unimodal, because here f dash x is less than 0. Also we can see that this PDF is unimodal. So please go. This is the shapes of PDF of arc cos distribution. It is decreasing and unimodal. This is the shape of hazard rate function of arc cos distribution. It is bathtub shaped and increasing. Next slide. Also, we derived its raw moments using this equation. Using this proportion, we can derive its raw moments. So this table represents numerical values of, that is, raw moments, variance, and coefficients of skewness and coefficient of kurtosis. From this coefficients of skewness, we can see that we will get both the positive and negative values for a coefficient of skewness, which represents that this distribution Both distribution has both right and left skewed shades. Also, we derived its art in complete moment using this proportion. Applications. For the application, we here we consider power distribution. That is, here we are comparing this new cosine distribution with the power distribution. Power distribution is also bounded on the interval 0, 1. Here we for comparing two distributions, we derived standard error minus log likelihood AAC, BAC, KS and its p-value. Also, we calculated its Anderson-Darling and Kramer-Mises values. This is our data set 1, which represents the times to infection of kidney dialysis patients in month. We converted this data set into bounded in the interval 0, 1. For converting this data set, I divide this old data set by 30. We will get a new data set. And next slide. We found that the minus log L, AAC, BAC, KS, and A star W star of ARCOS distribution is lower than that of power distribution. So this shows the flexibility of new distribution, ARCOS distribution. This is the fitted plots for data set 1. From this plot also you can see that this ARCOS distribution gives more flexibility than a power distribution. Is the next slide. This is our data set 2. We analyze the air data set on the failure times of air conditioning system of an airplanes in hours. We divide, yes, from this data. Also, we can say that ARCOS distribution gives more flexibility than power distribution. This is the plotter fitted plots for dataset 2. Yes, in summary, we proposed a no distribution bounded on 0, 1, and detailed study of this distribution are given. Moments analysis is performed, and the striking property of ARCOS distribution is that it can have increasing and bathtub shaped HRF, and also we analyzed this distribution using 2 data set. These are the references I consult.
Yeah, it's a simple, elegant, and nice presentation. Any question from the audience? Okay, if there is no question, then just I will put only one question. So what is the reason that you have selected the arc sign? So we have many more trigonometric functions, okay, integrated over different ranges will give you the value 1 so that it can be taken as a density. So what particular reason behind choosing arc sign?
Because this is bounded on 0, 1. Also, its flexibility is another reason for selecting this distribution. We can compare.
Yeah, by flexibility, I think you mean making them suitably either right skew or left skew, something of that sort. Is it so?
Yes, sir.
Okay, okay. Thank you, thank you. I think we can move to the next candidate. And the next candidate,
sir,
yeah,
sir,
please.
Sir, the second candidate on the wireless, sir.
Okay, no problem. I will move to the third one.
Sir, one more.
Yeah.
Sir, dear presenter, kindly switch on your camera while you're presenting your papers.
Yeah, please follow the instructions. So the third candidate is Devika, and the topic is the impact of inspection inaccuracy. Okay. please. Please carry on, madam.
Yeah, yes, sir. Am I audible, sir?
Yeah, audible. Please proceed.
Yes, sir.
Madam, kindly switch on the camera, please.
Yeah, sure, sir. Sure. Yes, sir. I think I am visible only, sir.
Yes, ma'am, it's visible. Yes, ma'am. Start.
Yes, sir. Yes, very good afternoon to one and all present over here. Myself, I'm Devika. Presently, I'm working as an assistant professor in Kalsingam University, and I'm here to present one of my research finding, that is the impact of inspection inaccuracy, that is inspection errors in acceptance sampling plan, how that inspection errors affect the shape of the OC curves, the operating characteristic curve. That study I have going to present here. And this entire study is carried out through one of the distribution, that is generalized Poisson distribution. So this is the overview of my presentation. First we have that introduction part. After that, inspection error and its impact in attribute acceptance sampling plan, and followed by that we have the conclusion part. So this is nothing but the objective of my study. Actually here I introduced one new distribution, that is generalized Poisson distribution. New distribution, this is new to this acceptance sampling plan area. So this is nothing but one two parameter generalized Poisson distribution as itself. It has two parameters, lambda one and parameters present in the Poisson distribution as itself. So coming to the introduction part, statistical quality control, as we all know that it's nothing but a process control system, and it consists of two parts majorly, that is product control as well as process control. So my study is mainly concentrated on acceptance sampling plan. That is nothing but one of the device for that product control methodologies. So this Poisson, the generalized Poisson distribution is nothing but it is one of the two parameter versatile distribution, and it has one of the most important properties, nothing but it possesses the over dispersed, equi-dispersed as well as under dispersed. These three kinds of dispersed conditions this distribution can handle. That is one of the most striking feature of this distribution. And next, sir, please, next page. Next page, sir. Introduction page already explained, sir. Yeah. Why this conventional distribution? There should be one reason why we need to go for generalized Poisson distribution rather than the traditionally existing distributions like Poisson distribution, binomial distributions like that. Because normally for selection procedures or designing sampling plans, generally Poisson distribution as well as binomial distributions are most widely used. So however, in some real life situations, the production processes will have some quality variations. That variations might occur due to some random fluctuations and all those reasons. So in such kinds of situations, we have to use some other distributions in order to handle those kinds of situations. So based upon Consol and J 1973, the generalized Poisson distribution can be regarded as a replacement for that traditional distribution. So because that is simple, the reason is very simple, because the generalized Poisson distribution can handle any kinds of dispersed conditions. The traditionally applied Poisson distribution can handle only equi-dispersed conditions. Whenever the mean variance based upon the relation between mean and variance, if mean is less than variance as well as mean is greater than variance means, that kinds of situations cannot handled by the Poisson distribution. So we have to use some other distribution. So that reason only I have opted here generalized Poisson distribution in deciding sampling plans. So this is nothing but, sir, next page, please. Yeah, this is nothing but the probability mass function of a generalized Poisson distribution. Here we have two parameters, lambda 1 as well as lambda 2. and in which lambda1 behaves as our mean value, and lambda2 is nothing but we take it as a dispersed parameter. That is, if that lambda2 equals to 0, then we can get that Poisson distribution as itself. So next page, please. This is nothing but the an efficiency proof. An empirical analysis of this introduced generalized Poisson distribution is carried out through an R programming language. That is, here we simulated one data over dispersed nature. So it's a Poisson distribution for testing this data. So in which I obtained the result that based upon that AIC, AICC and the BIC itself, we can make a conclusion that the GPD performs well. GPD means generalized Poisson distribution criterion values itself. We can make a conclusion that whenever the over dispersed conditions are existed or under dispersed conditions are exist in real life, the GPD performs well than that of Poisson distribution. So this empirical analysis obtained through our programming language gives us that evidence here. So next page. Next, sir. Again, next. Yeah, yes, sir. So this is nothing but the designing of single sampling plan under the conditions of generalized Poisson distribution. So this sampling plan, the designing sampling plan for this kinds of procedure actually assumes that there is no inspection errors, sir. That is, inspection is error free actually here. So here also we have made one comparative study between the Poisson distribution as well as generalized Poisson distribution for the same acceptance number or for same acceptance number as well as for the same probability of acceptance. The proportion defective we got for that generalized Poisson distribution is very less than that of Poisson distribution. So this is in general, how can we design a sampling plan based upon the generalized Poisson distribution in the assumption that here the inspection is error free. So this is nothing but the corresponding curves, the operating characteristic curves that we can obtain through the above corresponding tables.
Madam, can you make it fast?
Yeah,
you are running out of time.
Okay, sir. Yeah, coming to the inspection errors. If that inspection is error, if that inspection processes itself involves the errors, means how that affect the next page, please. How that affects the inspection. Sir, next page, that figure page. The last one, figure and the table page is this. Yeah, yes, sir, yes, sir. So from this figure itself, we can obtain, we can observe that whenever the inspection involves inspection errors, then how it affects the operating characteristic curve means for even a single 0% or 0.1% itself, when the probability acceptance get reduced drastically. So that's why we need to consider the inspection error percentage also there in order to make how that affects the shape of an operating characteristic curve. That is what this study actually means to highlight. That is whenever the apparent fraction non-conforming replaces the true fraction non-conforming, and evident changeover is happened in the acceptance probability. That is what this study mainly aimed to highlight. So that's also. Thank you. Thank you for this opportunity.
Yeah, thank you for your nice presentation. Any questions? Okay. Madam, could you just highlight why you have selected this particular area?
Why I am selected? Because my PG project work is also based upon the statistical quality control area, and in which specifically the product control area, sir. That's why I have just put that just to continue the processes in the PhD works also, sir.
Okay, nice. And in the process of your extension, did you face any difficulties in terms of numerical computing?
Yes, of course, sir. numerous complications are I have faced in calculating and simulating data actually.
What software did you use actually?
R programming. Yes.
Okay, it's very nice.
Yes, sir.
It's
Thank
very
you,
nice. You can conclude that. Okay. We'll proceed to the next candidate. Whether Manish Goyal is present here?
Yes, sir.
Yeah. Can you start? The topic
Yes,
is
sir.
a class of non-parametric test for testing of scale parameters.
Yeah. Good afternoon, everyone. Thank you for giving me opportunity. Myself, Dr. Manish Goyal, working as assistant professor in Department of Statistics, Postgraduate Government College, Sector 11, Chandigarh. So, topic of my today presentation is a class of non-parametric test for testing of scale parameters. It is a joint work with Professor Narendra Kumar from Punjab University, Chandigarh. Yes, sir. So, first of all, what is scale testing of scale parameter? As it has many applications in manufacturing, trading, agriculture, industry, and others. And the term scale, the scale parameter we use as a dispersion, scatter, or variability. So as we know, if we have the two or more methods, the one which gives the consistent results is always preferred. So that's why testing of scale parameter is very useful. And in this our test, we propose a new class of test for this testing of scale parameters. And we also compared it with some existing test to check whether our test is better or equivalent. And we also see a real life data example to see the implementation of this proposed test. Now, what is two sample scale problem? Let us suppose we have the random samples from two distribution as fx and gx, and we want to test whether if gx is equal to f theta x, that is there is a maybe there is a difference in their scale parameters. Then we want to test the null hypothesis that this theta is equal to 1. Means both have the same scale parameters, and against the alternative hypothesis that this theta is greater than 1. Means there are more variation in x as compared to y. So the literature view is that we generally use the Mood and Khatmi test. As we know in MSc or we use this, these are the well-known tests for this two sample scale problem. The other test, as we know, as modified by many authors. Now, why we made this new test? We made this new test, or we proposed this new journal class of test to have more efficiency and to make a new journal class of test. And this in this present work, we consider the ith order statistic of subsample size C from X sample and jth order statistic of subsample size D from Yth sample. As this is our proposed class of test, it is based on the symmetrical kernel Hij, which is given value 1 if ith order statistic of X sample is less than jth order statistics of Y sample, and C minus I plus 1th order statistic of X sample is greater than D minus J plus 1th order statistics of Y. And if opposite happen, we give the weightage as -1, 0 otherwise. And this is the U statistic associated with this kernel Hij, which is the just the average of all this symmetrical kernel. And we find it's a asymptotic distribution also, as under the null hypothesis, accepted value of this U statistic under H0 comes out this. Yes. So now we compare the proposed test with some existing test. We compare the proposed test of UCDIJ using the Pitman AREs, which is Pitman asymptotic relative efficiencies, with respect to the well-known test as the Mood 1954, Sukhatmi 1958, Joshi and Shetty 2008. We take some members of Joshi and Shetty, and also with the Mahajan, Gore and Aurora test 2011, which is shortened as MGA test. The results are given in from this table 1. As you see from this uniform distribution, whenever value is greater than 1, our proposed test is better. As you can see here, as our test is better from these tests which is taken at many sense. But the best value is to take C plus D, here the left side is C plus D, as maximum as possible. Like C plus D is 8 and I plus J as considered to be 2. Then we are getting the maximum efficiency. We are getting always the maximum greater than 1. So our test is always better in case of uniform. Next one is normal. In same pattern, we can see in the normal, like C plus D at 8, I plus J at 2, and we can see that in this row, all the values are greater than 1, like with respect to all the tests we have considered. So the same pattern in the Lossity distribution also, our test proposed is better in terms of Pitman ARE. And in terms of Laplace distribution also, it is the same. Sir, just 1 minute. Now in the Cauchy distribution, it is a very long tail distribution, as we know. So in the long tail, in this, as we take C plus D 8, I plus J 2, this comes out less than 1 with respect to the other test. So our proposed test is not, sir, please just 1 minute in the previous slide. Yeah, but our test is still better if we take C plus D and C plus D equal to 5 and I plus J equal to 3. So this is the best optimal choice of C plus D and I plus J, but still it is not better than MGA test. So yes, sir, next slide. So we can see that what is the performance of UCDIJ test, which is the proposed test. It is influenced by the tail behavior. Yes, sir. So we can say that if the distribution has very large tail weight, then take C plus D either 5 or 6 and I plus J equal to 3 to have the maximum efficiency. But MGA test is better than our proposed test. But if we have the other than very large tail weight distribution, then our test is always better if we take C plus D as large as possible and I plus J equal to 2. Yes, sir. Yes, sir. Now we implement our test based on a real life data set. Here we take the data set from the Hills et al. That is 1986, in which he considered a survey, and he takes a two group of students as 44 and 69 students, and they were asked to guess the width of a lecture hall in meters and feet. And we want to see if this guess of the width of a lecture hall, there is a lecture hall, and they want to guess the width in meter and feet. Whenever we guess the width in meter, there will be more variation, and when we guess the width in feet, there will be lesser variation. It is we want to check that. So we applied our test and find the p-value as 0.0062. As we know, p-value is less than 0.05, so we are rejecting the null hypothesis. And yes, and so we conclude there is greater variation if we have a lecture hall and we want to test whether there is a greater variation. Yes, we are rejecting the null hypothesis. So we conclude that there is a greater variation when we guess the width in meter as compared to guessing the width in feet. So we are getting that results. So these are the references I used here, which are the data set and the previous papers or previous test for this problem. Yes, sir.
Yeah.
Yes.
It's a nice presentation once again. Because dealing with non-parametric combinatorics is a very difficult task, wherein we don't have any smooth assumptions of distributional structures, or possibly even while we have the flexibility of doing our normal Newtonian calculus, all these things are done away with that. So you have to be very, very careful in dealing with the pure numbers, ramps, and combinatoric aspects. So in that sense, I think this is a very nice presentation. But any question from the audience? Okay, if there is none, I have one question in the sense that, see, you have proposed a statistic, okay, with a different structure, of course, involving some inequalities, that is without which we cannot do. Okay? But anyway, it's going to be different from the existing one, and you have also claimed by your comparison of real-time and other simulated data that your statistic is going to perform relatively better. But what made you to select this particular structure, and how it, in what way it deviates from the classical existing ones?
Yes, sir. We actually, we have, as you said, sir, there is no information given for the distribution. So we have to take the maximum information from the sample. So we make this structure as to get the maximum to maximum information from a given sample, because we don't know the distribution, as you say. So we have to take the maximum information. That's why we made this structure.
Yeah.
And it is a different one from the existing.
Okay, okay. Thank you very much. And it's an excellent presentation. Thank you.
Yes, thank you, sir.
I think we can proceed with the next candidate. The next candidate is Rachel Matthew, construction of selection of multiple deferred state repetitive group sampling inspection plan.
Yes, sir.
Yeah.
Is it audible, sir?
Yeah, audible.
Good afternoon, all.
Proceed.
Okay. Good afternoon, all. Myself, Rachel Matthew, doing PhD under guidance of Dr. S. Geeta, Department of Statistics, PSG College of Arts and Science, Coimbatore. And my topic of presentation is construction and selection of multiple deferred state repetitive group sampling inspection plan for variables. And the next slide, sir. The contents included in my presentation are introduction, sampling plan by variables, multiple default state, repetitive group sampling inspection plan by variables based on normal distribution, both unknown case and known case, mathematical expression for operating characteristic function, example, operating characteristic curve, comparison, and conclusion. Introduction. At present scenario, the quality of manufactured products plays an important role in seeking the attention of any consumers. So in order to ensure such quality requirement by manufactured products, the manufacturing processing unit will check the quality either using 100% inspection or sampling inspection. And in sampling inspection, the acceptance or rejection of submitted lots are usually based on sample data. And sampling plans are the plans that are used for making such inspecting procedures. And next, classification of sampling plans. Dodge have classified sampling inspection plans into 4 main categories, namely, first one, lot by lot sampling inspection plan by attribute, lot by lot sampling inspection plan by variables, continuous sampling inspection plan of flow of units by attributes or variables, and special purpose sampling inspection plans. So next slide. Sampling plans by variables. In variable sampling plan, instead of we are simply classifying the data as conforming or non-conforming, we are measuring the sample units for particular specified quality characteristic, and hence it is applicable for measurement data. And the advantages of this variable sampling plan are, it is more providing more information regarding the data, and it requires small sample size than attribute sampling plan, and providing a better protection as that of the attribute plan. And the basic assumptions under which we can apply the variable sampling inspection plans are: quality characteristics should be measurable on a continuous scale. The functional form of distribution function of quality characteristic must be known. Quality characteristics should have upper specification limit or lower specification limit or both. If X is greater than upper specification limit or less than lower specification limit, we will classify the item as non-conforming. Otherwise, it is classified as conforming. These are some literatures on variable sampling plan. So next slide. Multiple deferred or dependent state sampling plan. This plan was proposed for attribute plans by Wortham and Baker in 1976, and it is one of the conditional sampling plan. And the conditional sampling plans are those which use the information from neighboring lots for taking a decision on current lot. Neighboring lots in the sense either past lot or future lot. So if the plan is making use of information from past lots, those sampling plans are called dependent or chain sampling plan. And if the plans are making use of future lots for making decision on current lot, it is called deferred state sampling inspection plan. Next slide. These are the assumptions under which we can apply this multiple deferred state sampling plan for variables. Regarding production, the production should be steady so that the result of current lot and future lots are indicative of continuing process. Regarding lots, it is submitted in the order of production, and operating characteristic function is determined, and hence the curves are drawn for inspection by variables, and the characteristic should follow normal distribution. Next slide. Next, variable repetitive group sampling plan. The RGS plan are developed by Sherman and is applicable for lots submitted serially in the order of production, and it provides additional chance to the lot in default state to be accepted or rejected. Next, it is the proposed plan, which is variable multiple default state repetitive group sampling plan, and usually it incorporates the features of both the existing multiple default state sampling plan developed by Wortham and Baker and repetitive group sampling plan. The operating procedure. The first step is we have to take a random sample of n units from the submitted lots under inspection, and we have to measure each of these sampled units, and we have to record the measurements as say x1, x2, etc., xn, and from this measurements we have to evaluate the sample mean x bar, and we have to evaluate a statistic v equals u minus x bar by sigma, where u is the upper specification limit. If lower specification limit is specified, we have to evaluate the statistic as x bar minus L by sigma, where sigma is the non-standard deviation. And in the third step, we will take decision regarding the lot, that is, we will accept the lot if the statistic is greater than or equal to Ka sigma, which is the unconditional acceptance constant, and we will reject the lot if V is less than Ka sigma, which is the conditional acceptance constant. And if this statistic lies between Kr sigma and Ka sigma, we will go for succeeding or future M sigma lots, and if all these M sigma lots are accepted, we will accept the lot. Otherwise, we will repeat sampling until we will reach a decision. And next case is when sigma is unknown, the operating procedure is same as that of non-sigma case, and the only changes we have to replace the standard deviation sigma by capital S, where capital S square expression is given over here and is an unbiased estimator of population variance sigma square. So next slide, please. Operating characteristic function. First of all, we have to define what is lot quality. The lot quality is expressed as P equals, as mentioned in the assumption part, probability of X greater than U, and on simplification, it will reduce us to 1 minus phi of U minus mu by sigma. And if lower specification limit is specified, then P will become probability of X less than L, and on simplification, it reduces to phi of L minus mu by sigma, where phi is the cumulative distribution function of standard, normal, variate. And the operating characteristic function is nothing but the probability of accepting the lot under the given procedure, and the expression is given over there, that is, and the optimum plan parameters are determined by specifying the 2 points on the OZ curve, namely AQL 1 minus alpha and LQL beta, by minimizing the average of average sample number. AQL is the acceptable quality level, LQL is the limiting quality level, alpha beta are respectively producers risk and consumers risk, and the expression for average sample number is given over here. So next slide, please, sir. Variable multiple deferred state sampling plan when sigma is unknown. It is more complex to administer, but it is more realistic. So we have to go for that. And the optimal plan parameters are evaluated in a different manner. It is based on the sampling distribution of X bar plus or minus KAS into capital S. And Duncan in 1986 have proved that it is asymptotically normally distributed with mean mu plus or minus KAS sigma and variance sigma square by NS into 1 plus KAS square by 2. So next. Operating characteristic function, the expression is very same as that of non-sigma case. Only changes we have to replace sigma with capital S, and the plan parameters, as mentioned before, it is determined by specifying the 2 points on the operating characteristic curve. So next slide. An example is provided over here. Suppose the desired protection is given at AQL 1.5%, LQL 4.5%, and alpha beta 5% and 1% respectively. And for M equals 1, the required plan parameters when sigma known and unknown sigma along with the average sample number is obtained over here. And from this we can infer that when sigma is known, the average sample number as well as the sample size are comparatively smaller. So next slide. Operating characteristic curve is provided. Next slide. Comparative study have been carried out here. We have compared our proposed plan with variable multiple deferred or dependent state repetitive group sampling plan developed by Jayadurga and Balamurali in 2020 and is compared with respect to average sample number. For example, for the specified AQL and LQL values and alpha and beta, we have obtained our ASN for non-sigma case and unknown sigma case as well as the optimum plan parameters. And next slide, sir. For the same values, the parameters have been taken from Jayadurga and Balamurali 2020 paper as follows. And from these 4 set of values, we can observe that ASN as well as the sample size is comparatively smaller for our proposed plan.
Madam, can you make it?
I'm concluding, sir. ASN curve have been drawn for non-sigma case and unknown sigma case. Next slide, sir. Next. Conclusion, and I'm concluding myself, that is a multiple deferred state repetitive group sampling inspection plan under assumption of normal distribution is proposed, operating characteristic function is derived, and proposed plan provides better protection regarding producer and consumer, and it requires small sample size as well as ASN. Codings can be developed for obtaining the optimum plan parameters. These are some references that I have gone through. Thank you, sir.
Thank you, madam. It's a nice presentation. Can you move to any questions from the audience? Okay, can you move to the conclusion slide?
Yeah. Previous, sir.
Yeah, please. See, it is mentioned that a multiple deferred state repetitive group sampling inspection plan under the assumption of normal distribution. Okay, so if the samples come from normal distribution, what are all the possible deviations that you expect in your estimates?
That is, the sample size will be a little bit higher, and usually that we are doing that work for future works, actually non-normal distributions. The sample size and ASN will be a little bit higher than this.
Okay. Yeah, that's what is expected. Okay, fine. It's a good presentation. And the answer is also up to the mark. Good. Okay, I think we can move to the next candidate, and
Thank you,
the
sir.
name is, yeah, please. Next candidate is Deepa Koshi, modeling gastric cancer incidence through beta exponentiated exponential distribution. Whether the candidate is present. Deepak Koshi.
Yes, sir. Yes, sir. Yes, sir.
Madam, can you please proceed? Madam, you can start.
Sir, I'm Deepa Koshi, a research scholar in Department of Statistics, Annamalai University, and working with Dr. P. Pandian, Annamalai University. My topic is modeling gastric cancer incidence through beta exponentiated exponential distribution. Sir, next slide. Sir, my abstract is the introduction. A suitable parametric model is of great interest in the analysis of survival data, and it provides an insight into the characteristics of failure times and hazard functions that may not be available with non-parametric methods. The Weibull distribution is one of the most commonly used families for modeling lifetime distribution, mainly cancer survival data. Here I introduce a new distribution called beta exponentiated modified Weibull distribution, and I model the distribution. I model the distribution with that, model this data with that distribution. The cancer is the biggest burden. For a parametric estimation, the estimation was collected from the hospital records of Cancer Center in Pathanamthitta district in Kerala. Stomach cancer incidents during 2018 to 21 was collected and used for further studies. The data collected supports the previous studies based on the UK Cancer Research Institute and the National Cancer Registry Program, NCRP, 2010 conducted, it suggests that the stomach cancer incidence increases with age. Out of 85 patients in my study with stomach cancer, 22 are above 75, and out of these 16 are male patients. And for above age 75, the rate of incidence is 25.89%. That is about 1/4 of the total patients falls in the age group above 75. My analysis is my data collected was like this, and it is graphically expressed in this way. And we can see that in above 75, the male patients are, the number of male patients are very high. And the rate of incidence of stomach cancer is also plotted. Even though this model describes age at diagnosis and gender are the main factors relating to the cancer incidence and survival rate, there are so many other factors like poor dietary, use of smoke, excessive use of tobacco, biological processes like DNA damage, ill health, due age, etc. affects cancer scenario. So it is better to explain the behavior of this data with the help of a distribution with more parameters than Weibull distribution. Hence, a 4-parameter distribution, namely beta exponentiated exponential distribution, is used for the cancer study. The probability density of BEMW distribution, which is a 6-parameter distribution, and I derived the BE distribution from this. It is observed that the PDF of BEMW distribution assumed exponential skewed to symmetric shape, and depending on the values of the parameters, this distribution is introduced by Misra Naviz Shahs in 2019, and this distribution contains 19 lifetime distribution as special cases. BE distribution is one such special case of this BMW distribution. Here in the above distribution, there are 6 parameters, and if delta equal to 0 and lambda equal to 1 in the above density, it gives a BE distribution which is derived from the BMW distribution. Its probability density function and its cumulative distribution function are also given. Its survival function and hazard rate functions is also derived. And next slide, sir. Its parameter estimation is done through the Python programming, and the parameters of the model are estimated using maximum likelihood method of estimation. The approximate parameters are, sir, previous slide, please. Alpha cap, beta cap, gamma, and there are 4 parameters. The 4 parameters are estimated, and the density function is like this. The PDF of this BE distribution and observed values are plotted. Also, its survival probability of BE distribution and observed values, and also its hazard rates are plotted. And you can see that it is better approximation than a Weibull distribution. Comparison studies I have already done, and it's not presented in the slides. I think this model gives a good approximation to the data set that the disease is dominant in 65 to 75 years. For younger age persons, the survival is high for healthy patients, and the survival probability decreases as age increases, and the shape of the hazard function curves indicates that there are situations such as the survivability after surgery, where risk quickly increases due to the chances of complications such as infections, and there decreases the patient's risk of recovers. I make a suggestion with the doctors in the hospital, and they suggested the same thing like this. Thank you, sir.
Okay. So again, yeah, very good presentation. But the only problem, as you already mentioned, it is not supported by any simulated work or real-time data you have compared with the other distributions to claim that this is relatively better. But that's the most important part of any research activity or presentation, so to say. So it's always better that you support, because you are giving you are saying that this distribution is going to serve better compared to the so at least you can compare with the classically existing one, something like Weibull or exponential, something of that sort.
Okay, sir.
So if that is going to be the case, then it would have been very fine. And one more thing about increasing the number of parameters. You mentioned that a particular distribution with many parameters, okay, that is a generalization of some 18, 19 distributions you are saying. Yeah, you see, with suitable hypothesis, we can prove anything on Earth. This is a statement, okay? So if we increase the number of parameters, we can increase also a large family of distributions. But the problem is we have to make a compromise between the number of parameters and so the data structure, because we don't have sufficient data to estimate all such parameters. So we have to have a parsimonious structure in which you should have a balance between the data size, I mean sample size, and the number of parameters. So in that sense, I think this will give some idea for young researchers to seek a balance between them. Okay, yeah, I think you have done, and it's good.
Okay, sir.
And I think we can move to the next candidate. Next candidate is Mrs. Saranya. The topic is multiple dependent deferred state sampling plan for variables based on Laplace distribution. Whether the candidate is present here? Yeah. Can you proceed? Saranya, can you unmute and proceed?
Good afternoon, sir. I am Saranya, research scholar in the Department of Statistics, PSG College of Arts and Science, Coimbatore. Under the guidance Dr. S. Geeta. My topic is my multiple dependent states variable sampling plan for Laplace distribution. Next one. Abstract. The sampling inspection is an activity for taking decisions on one or more lots of finished products which have been submitted for inspection. The decision of either acceptance or rejection of the lot is usually taken under implementing suitable sampling inspection procedures called acceptance sampling plans. Or one of the acceptance sampling inspection plan is variable sampling plans, which are intended for quality characteristics that are measured under continuous scale and is known to have a distribution of a special type. Say it is known to be normally distributed. method. The multiple dependent state sampling plan belongs to the conditional sampling procedures in which acceptance or rejection of a lot is based not only on the sample from the present lot, but also on the sample results from the previous lots. In this article, a variable multiple dependent state sampling plan for accepting lots of products whose characteristics follows a Laplace distribution is proposed. The sampling plan is designed by considering the 2 points on OZ code, and tables are constructed for the selection of parameters indexed by acceptable quality level and limiting quality level, with associated with the producer's risk alpha and consumer's risk beta. The parameters of the proposed. Next, introduction. Acceptance sampling is a method of measuring random samples of populations called lots of materials or products against the predetermined standards. Acceptance sampling is a part of operation management or accounting, auditing, and service quality supervision. It is important for industrial but also for business purposes, helping decision-making process for the purpose of quality management. There are 4 types of acceptance sampling. There are lot by lot sampling by attributes, lot by lot sampling by variables, continuous sampling method, and special purpose sampling plans. Here, variable sampling plans use the actual measurements of the sample products for decision making rather than classifying products as conforming or non-conforming as in attribute sampling plans. The major advantage of variable sampling plans are: first one is the equal protection to an attribute sampling plan with a smaller sample size. Then variable sampling plans allow the determination of how close to nominal or specification limit the process is performing. A variable sampling plan are intended for quality characteristics that are measured in a continuous scale. When destructive testing is employed, variable sampling plan is particularly useful in reducing the cost of inspection. Multiple dependent state sampling plan. The concept of multiple dependent or deferred state sampling plan was introduced by Werthmann and Baker in the year 1976, which is one of the conditional sampling procedure. In this plan, the decision on accepting or rejecting of a lot is based on the sample information from the current lot together with the consecutive preceding lots or from the upcoming lots. The multiple dependent sampling plan is applicable in the case of type B situations, that is sampling from a continuous process. Where lots are submitted for inspection serially in the order of production. Later, Warest further modified the operating procedure and characteristic function of the multiple deferred state sampling plan, which was introduced by Werthmann and Baker for attributes to make it on a pair with chain sampling plan. A variable MDS plan inspection plan is defined under the following assumptions. Lots are submitted for inspection serially in order of production from a process having a constant proportion non-conforming. The consumer has the confidence in the supplier, and there should be no reason to believe that a particular lot is poorer than the preceding lots. The quality characteristics follows a normal distribution. A multiple dependent state sampling plan by variables is proposed for Laplace distribution. The Laplace distribution is a 2-parametric symmetric distribution, which is also known as double exponential distribution. Next, these are the some reviews on variable MDS plan based on Laplace distribution. The PDF for Laplace distribution is given here, and the cumulative distribution function is also given. The mean and variance are variable MDS plan for unknown sigma. The quality characteristic of interest has a upper specification limit U, follows a Laplace distribution with mean 0 and standard deviation pi by √2. The operating procedure of a proposed variable MDS sampling plan is as follows. First step is from each submitted lot, take a random sample of size n and compute V equal to U minus x bar by S, where x bar and S are given here. S square is an unbiased estimator of sigma square. Second step, accept the lot if V is greater than or equal to Ka, and reject the lot if V is less than Kr. If Kr is less than V or less than Ka, then accept the current lot, provided the foregoing M lots were accepted on the condition that V is greater than or equal to Ka. Thus, the proposed unknown sigma sampling plan is characterized by 4 parameters, namely N, M, Ka, and Kr. If Ka equal to Kr, then the proposed plan reduces to single variable sampling plan with unknown standard deviation. Sampling plans are designed by considering 2 points on the OZ curve, namely P1, 1 minus alpha and P2, beta, where P1 and P2 are termed as acceptable quality level and limiting quality level associated with producer risk alpha and consumer risk beta respectively. Now, the OC function of the variable sampling plan is given here. Here, the first term in the right hand side represents the probability of accepting a lot based on the current sample, and the second term represents the probability of accepting a lot based on the states of the preceding lots. The AQL and LQL are defined by the formula here. Next, please. For a specified AQL, 1 minus alpha and LQL, beta, the designed parameters of the proposed plan may be determined by satisfying the following two conditions, and the formulas are given here. Here omega 11 be the value of omega 1 at P equal to AQL, and omega 21 be the value of omega 2 at P equal to AQL. Omega 12 be the, then this is the minimizance. These are the constraints used here to solve the non-linear optimization problem. The routine FMINCON in the MATLAB software was used which is based on the sequential quadratic programming algorithm proposed by Disodial and Wright. The value of M is fixed as some integer and solve the problem separately to reduce the number of decision variables. Values of the parameters for several combinations of AQL and LQL under alpha equal to 1.05 and beta equal to 0.10 are calculated. It is also observed that the proposed plan becomes infinity. The proposed plan becomes single sampling plan when M goes to infinity. Example: suppose that it is preferred to set up a MDS sampling plan by giving a protection to the consumer and producer in terms of quality levels P1 equal to 0.01 and beta equal to 0.05 associated with alpha equal to 0.05 and beta equal to 0.10. When the quality characteristic is distributed according to a Laplace distribution, then the parameter values are N is equal to 5, K is equal to 2.35, Kr equal to 1.77. When M is equal to 1. For each submitted lot, take a random sample of 15 and compute V and accept the lot if V is greater than or equal to 2.3501 and reject the lot if V is less than 1.7753. If 1.7753 is less than or equal to V less than or equal to 2.3501, then accept the current lot provided the preceding lot was accepted on the condition that V is greater than or equal to 2.3501. Next, please. Here, variable sampling plan of variable MDS plan for known sigma. The quality characteristics of the upper specification limit view and follows a Laplace distribution with mean 0 and standard deviation pi by root 2. The operating procedure is as same as the unknown sigma. Instead of S, here we use sigma. The probability of acceptance P of P is defined here, and the probability of lot is rewritten here. For specified AQL and LQL, the designed parameters of the proposed plan may be determined by satisfying two conditions PA of P1 and PA of P2, where W1 which is the formula is as same as the unknown sigma plan. Here the constraints are given to in this case also we use the FMINCON in the MATLAB software which was used in the based on the sequential quadratic programming algorithm proposed by Disodial and Wright. The value of M is fixed as some integer and solve the problem separately to reduce the number of decisions. The value of the parameters for several combinations of AQL and LQL under alpha equal to 5% and beta equal to 10% are calculated. It is also observed that the proposed plan becomes single variable sampling plan with parameters when n goes to infinity. The example, suppose that it is preferred to set up an MDS sampling plan given protection into a consumer and producer in terms of quality levels AQL equal to 0.01 and LQL equal to 0.05 associated with alpha equal to 5% and beta equal to 10%. When the quality characteristics is distributed according to Laplace distribution, then the parameter values are N is equal to 4, K equal to 2.3661, Kr equal to 1.5731 with when M equal to 1. For each submitted lot, take a random sample of size 4 and compute V. Accept the lot if V is greater than or equal to 2.3661 and reject the lot if V is less than or equal to 1.5737. If 1.5737 is less than or is equal to V less than 2.3661, then accept the current lot provided that the preceding lot was accepted on the condition that V is greater than or equal to 2.3661. Conclusion. The intention of this paper is to develop a multiple dependent state sampling plan for accepting lots of products whose quality characteristic follows Laplace distribution by given location parameter mu is equal to 0 and scale parameter pi is equal to 1. The proposed variable MDS plan provides a better production than conventional single and double variable sampling plans with smaller sample size. It is also observed that the proposed plan becomes single variable sampling plan when M goes to infinity. These are the references which I made. Thank you.
Yeah, it's a very good presentation, starting from the explaining the definition clearly and proceeding gradually and also mentioning some special cases wherein this reduces to a single sampling. Any questions from the audience?
Vishwanathan, can I ask one question?
Please proceed.
One suggestion, yeah, because of the time, the presenter is rushing all the slides. That's good. But my question is very simple, Ms. Saranya. You use the Laplace distribution. Do you think that the Laplace distribution is stable?
Yes, sir, it is a symmetrical distribution. Laplace distribution is a symmetrical distribution.
When do you claim that, because symmetrical is nothing but the normal. In stable condition, when you use the normal distribution, it's nothing but the normal distribution is symmetricity. But during the normality period, when you are using the Laplace distribution, it's not going to be a stable one for any problem. So you have to consider the geometric distribution so that you have to come up with the stochastic modeling. That's a big issue, because I see that here you're considering the normality assumptions. But when you're considering the normality assumption using the Laplace distribution, whatever the examples you used and the parameters you are estimated, that value may not be a stable one in a practical situation. So please consider that.
Okay, sir. Thank you, sir.
It's a welcoming question in the sense that such questions throws more light on the concept, which will be useful for the presenter as well as the audience. Any other question? Okay, yeah. Then I think we will proceed with the next next candidate. Thank you. The next candidate is.
Sir, next one is Manjula, sir.
Okay.
Manjula.
Yes, you can proceed, madam. Is the candidate present?
Manjula, madam. Yeah, Manjula. Sir, shall we move to next?
Yeah, next. Yeah, that's better.
Jeevita.
Yes, sir.
Yeah, we can proceed with the topic is universal optimality of circular exercise.
Yes. So good afternoon, all of you. This is Jeevita from Department of Statistics, Loyola College, Chennai. And my topic is universal optimality of circular neighbor balance design under equal right and left effects when the observations follow autoregressive process of second order. So here, this paper is to study the optimality of CNBD for total effects when equal right and left neighbor effects are present in the model. And of course, the observations are correlated according to AR2, C. So when we just take the example, few examples. So in many practical problems, it is unavoidable that a particular plot is being affected by neighboring treatment effects. Even though it is harm in many cases, the plot is being gained by neighboring effects in few cases. And the neighbor designs provide a tool for local control in many places. So neighbor effects, either it could be a natural one or due to layout of plots, can deprive the result from its representativeness. Therefore, it is important to control it through design and analysis. And in field experiment, okay. And it started in the year 1967 when we started to study a technique used in virus research which requires the arrangement in circles of samples from a number of virus preparations, such that over the whole set, a sample from each virus preparation appears next to a sample from every other virus preparation. So he started to study about the circular designs. And here in this slide, I have just given the basic definitions of the blocking design, what is blocking, and then what do you mean by circular designs. So you know very well in design, blocking plays a vital role because it is one of the important local control technique. It helps us to reduce the variation present in the design. And if the two extreme plots are neighbor of themselves, then you can just bring the concept of circular designs. And see, an optimal design, it is actually a group of best design points selected when reducing or augmenting the number of experimental runs in the original design. Therefore, and there are several optimality criterion in the choice of an experimental design. For the moment of many criteria, we are interested in deriving an optimal design for estimating the underlying regression model. So that is the specific aim of the experiment is to estimate the model parameters with high precision. So here it means estimating the model parameters must have minimum variance and covariance. Next slide. Next slide, please. Yes. And these are the few literatures reviews which we have gone through. And so here we have just given the basic definitions and the notations which we require to obtain the optimal designs. So of block designs, neighbor block designs, and circular binary block designs, these are the basic definitions of the designs. Okay, and yes, so here we have taken the PyP optimal design. So like the optimality criterion is obtained based on the trace of the information matrix. So here we have defined the function pi from the set of information matrices to a real valued number from -infinity to +infinity. So it must satisfy the three conditions. The first one, pi must be convex, and phi of BCD is non-increasing as B increases, and phi of CD is invariant under any permutation of rows and the same permutation on columns of CD. And here the very basic definition of the optimal design, like as I have mentioned, it was obtained from the trace of the information matrix. If the trace of the information matrix is maximum, then that particular design can be considered as the optimal design. So using that condition, we started to obtain the optimal designs. And this is one of the important theorem, the general equivalence theorem in the literature. If you want to say a design to be optimal, so if these three conditions are satisfied, then we can say design to be an optimal. The design minimizes phi of C, and the minimum of phi of C must be greater than or equal to 0, and the derivative phi of x comma xi star achieves its minimum at the points of the design. So this theorem provides the methods for the construction and checking condition for optimum designs. And we can also discuss the efficiency of the design. Yeah. So here I have taken three models. The first one, if a particular design is affected only from one of its neighbor, okay, which means it has only one neighbor, then the total yield can be obtained from the total effect and from the left neighbor, okay, either left neighbor or the right neighbor. In the second case, a particular plot is affected by both the neighbors, which means it has two neighbors, left as well as the right. And the third case, if both the neighbors, left as well as right, if both the neighbors are giving the equal importance to a particular plot, then what happens? So these three are the models which we have handled in constructing the optimal designs. But here in the particular paper, we have just taken the second order model with with second order autoregressive stationary process. So here for this particular model, we have taken the yes, okay, and this lemma is an important one to obtain the optimal design. So let CD of alpha be the information matrix for some effect alpha based on design D, and assume that the design D star as its information matrix completely symmetric. Then D star is universally optimal for the effect alpha or the class of designs if and only if trace of CD star must be equal to maximum of all the traces of CD of alpha. So here, as I have mentioned, we are considering only AR2, C with equal right and left neighbor effects. So like this theorem helps us to obtain the trace of CDU, which actually maximizes, which is the maximum one, so that this particular trace can be used to obtain the optimal design. So here for 3 less than or equal to k less than t, CNBD of 2 in omega is universally optimal for total effects in the model M3 among all the designs with no treatment neighbor of itself. When 0 less than or equal to rho less than 1, and among all the designs with no treatment neighbor of itself at a distance 1 or 2, when -1 less than rho less than 0. So for this particular case, we have obtained the trace of CDU as this expression. Here we have Ni to be the number of occurrence of treatment I in the sequence L, and Mi is the number of times treatment is on the left-hand side of itself in the sequence, and Pi to be the number of plots having treatment I both on the left-hand side as well as on the right-hand side of the sequence L. So we have the proof of this particular theorem. So here we consider the information matrix as submatrices CD11, CD12, and CD22. For this, I obtained the S curve. And next slide, please. Okay, so we have got the expression for S curl as this one, and using this expression, we obtain the trace of the information matrix. Yes. So next slide, please. So these are the derivations which we have used. Yes, you
can you make it fast?
Yes. So this is the expression we have got. So this actually minimizes this. This is a maximum value of all the traces. And the same thing we can. Yes. Next slide, please. Yes. So same thing we can do when we have both left as well as the right neighbor effects. So in this case, we will be having CD11, CD12, 13, 21, 22, 23, and 31, 32, and 33. Yes. So for this also, we have got the trace of the information matrix. Yes. So from which we can obtain the optimal design. Yes. And I also have placed the references which we have used in deriving this result. And thank you so much, sir.
Yeah, it's a very exhaustive presentation, so to say. And any questions from the audience?
Shunadan, again,
Yeah,
Bala here.
Please,
Can
Professor, please. Yeah, you can proceed.
Dr. Jivita, it's abundant theory involved in this research. Thanks to it. But I'm trying to understand your theory to a practical point of view. In the beginning, you mentioned that you want to minimize the variance of all the parameters in the model, in the regression modeling, and then you list out 3 equations where left and right, and then the interaction effect.
Yes.
I'm thinking about in a real life situation where I have a plot. In the middle of the plot, there is a paddy yield, and left and right is the sugarcane and banana. And the another plot, I have a paddy, but there is on the left and right is some kharif plants.
Okay, sir.
But how do you get to give me an explanation about the model relate to this example? How you are going to increase the yield, how you are going to minimize the error in the model?
Okay, so sir, here definitely the paddy plot will not be obtaining the equal effects from both the banana as well as from the other plant. So in this case, the paddy yield will definitely be affected by the effect of maybe the fertilizer or any other manures which we use for paddy will be getting affected by the neighboring plots. So in order to obtain, in order to minimize the error, or in order to maximize the yield of the paddy, we may have to think of some other plants which may not take maximum the effect from the paddy field.
One thing, maybe you think about this way, both banana and sugarcane need more water, right?
Okay.
And you need more fertilizer.
Yes,
And you're providing the same amount of water to the paddy in between. And another plot, I have the paddy with a controlled environment and giving the water, but the neighboring left and right is say some other crop which does not require water. So do you think that comparing to the first plot to the second plot, I will get more yield than the first one because you have more water, you will get more yield? I'm thinking, in a different scenario. That's what you just think about it. Now, no need to answer it. But these are the scenarios, in practical scenarios, you have to think about when you're putting in the model sense. Because there are so many factors associated with it, just not the interaction effect or the multiplicative effect in the model. Thank you. Very good theoretical representation.
Thank you so much, sir.
Yeah, it's a good observation from Professor Bala in the sense that I too was thinking to some extent in the same lines. And it is not a matter of fact whether which particular crop you have to select in the neighborhood, but having that neighborhood, we have no control over the neighborhood. So we have to make adjustment for the neighborhoods, okay, using this design and arrive at a conclusion saying that this requires, this comes out with good yield compared to a control, as Professor Bala was mentioning.
Yes.
So that is one thing. And one more thing is, I have a problem in the sense that you are saying that the neighborhood affects, okay, and you have considered left and right. And is there a possibility that something like the effect of left and right neighborhoods neutralizes themselves and leads to a normal design? Is it possible? So in your model, okay, I will not go into the practical aspect. Just I will consider the theoretical aspect itself by suitably adjusting the parameters. Say something like your neighborhood effect is alpha, and the right neighbor is alpha, and left neighbor is something like minus alpha.
Yes, sir.
And if they are offsetting each other, then is there a possibility that the things reduce to a classical design?
Yes, sir, definitely we may have. Then in that case, the yield is not affected by the neighboring effects.
Yeah, that's what I'm asking. All your deductions and getting the trace of an information matrix minimizing. So will it trivially reduce to a classical minimization procedure? Is it so?
I have to work on it, sir, because I didn't think in that. I'll just include this part. Maybe I can try, sir.
Okay, Professor. I think it's a very good presentation with provoking so many questions. Okay, as the number of questions is more. It's a degree of probably your hard work. So
I may work on it further, sir. Definitely.
Yeah, and one more thing about while seeing the reference and initial work, I see Professor Santaram's name there.
Yes,
and he was the one who taught me design of experiments when I was there in my second semester or first semester in my UG in 1983. It also triggered my memory.
He's my guide. He's my research. He's my PhD guide, sir.
Okay. And we are missing him. And
yes, sir, definitely. I have to actually make a word because of his work. He started these works, then I started working on it.
Yeah. Okay. let us pray for the best.
Yes.
Okay, I think we will move to the next candidate.
Thank you so much, sir.
Yeah, welcome, madam. So the next candidate is Rajesh Kumar, a study of unstabilized production process by monitoring fraction non-conformities.
Good evening, everybody.
Yeah.
This is Rajesh Kumar. I am doing my MPhil at Government Arts College, Coimbatore, under the guidance of Dr. Deva Rules. My study topic is a study on unstabilized production process by monitoring fraction non-conformities. I have taken the truncated distribution of discrete distributions. In statistics, a truncated distribution is a conditional distribution where we restrict some domain of some other distributions, probability distributions. The concept of truncated distribution plays a vital role in a variety of production process, optimization, and quality improvements. A reason for truncation may be of interest. There may be no interest beyond the truncated point. Truncated and normalized as long as the distribution is a good distribution of the data. Another reason for truncation is that the distribution is not valid beyond the truncated point. Truncated distribution will introduce some errors. It may be small enough to ignore. If it is suspected to be a major issue or cannot be ignored, we may use some other distribution for the study. We use truncated distribution in cases for production control and quality improvements, etc. Truncated distribution arises in practical situations, statistics, in cases where the ability to record about occurrences limited to a value which lie beyond the below or above the given threshold. Truncated distribution. To truncate distribution is to restrict the value of an interval and renormalize the density function. The integral over the range should be 1. The main reason for truncation is, for example, if you take the case of death of newborn babies, it will be more during the first year or second year. So when we take some study based on this, we can restrict 1 or 0 or first year in our cases. Also, for example, number of divorce cases we take, it will be more during the first year of the marriage because of misunderstanding and impatience between the couples. If we restrict 1 or 2 years and then we check the cases, it will be less, or maybe there will be some reason for the divorce. This is the slide shows the truncated distribution based on binomial distribution at x is equal to 0 and 1, which is derived, and mean and variance are given for both binomial and Poisson distributions. This is for Poisson, x and 1. Next slide, please. In this case, we are taking a problem which the number of samples and sample sizes are given. Sample sizes are varying sizes which are given here, and the number of defective capacitors are given. We have to find the control shot and conclude based on the truncated distribution. In our case, I take the truncated distribution at x equal to 0 based on binomial distribution, which I calculated the average sample number and average fraction defective p bar, and we use the truncated binomial distribution at x equal to 0 for the case of this study. And I calculated the mean based on the binomial distribution at x equal to 0 and x equal to 0, mean and variance, which I used in upper control limit and lower control limits, center limit for calculation. based on the data, I calculated the fraction defectives, and based on the control limits which I derived from the binomial distribution at x equal to 0, truncated distribution at x equal to 0, which I draw the chart where the control limits are given here. Since LCL is negative, it is taken as 0, and all points which fall under this control limit, and we conclude the process is in control. Thank you.
A very good, within time and non-confusing presentation, so to say. Okay. Any questions from the audience? Okay, if there are no other questions, then we should appreciate the effort of Rajesh Kumar. I hope he introduced himself as a MPhil scholar, right?
Yes.
Yeah. So yeah, at this level, I think this is a wonderful effort. Okay, I can imagine if such brilliant students comes to PhD, I think it will be manifold, so that the output will be much more we expect. And this is a very beautiful presentation. And one question from my end. Okay, it is. See, you are using a truncated structure here. Okay, have you compared using the same without truncation? That is, have you made any